TAG strength by hip post-treatment, we found that the validate constant of the TAG strength is about 50.9 at 70 nanometer, and the absorption coefficient of this material is as low as 2.5 by 10 to minus 3 per centimeter. So we can find the maximum power is about 1.2 kilowatt, which is much higher than that of TG single crystal. And however, the size of the prepared TAG ceramic is still not large. So we will further improve the length and the optic of the TAG ceramics. So in order to improve the optic quality of the TAG ceramics, we are always think about the some composition design. For example, we want to partially replace the turbine 3 plus by Eternal Brass to form some anti-size defects, because with higher anti-size defects concentration, which will increase the solid solution range and also suppress the signal phase in the TAG ceramics. So we also prepared such TYAG ceramics by solid state reactive method by using some oxide powders as starting material. For example, yttrium oxide and terbium oxide, terbium 4, oxygen 7. And also high purity alumina as the powder. We prepared such TYG ceramics by almost the similar process with TAG ceramics. We can find that we prepared finally, by solid state reaction method, we prepared such TYG ceramics. We can from the XRD pattern that with the increase of the ethyl content, the lattice parameter and the theoretical density both decrease. And we from the SEM observation, and we can also draw a conclusion that with the integral substitution, the signal phase in TAG ceramics can be effectively suppressed, and because the elimination of such signal phase, so the grain size of the TYG ceramics increased because of the elimination of the pinning effect. So we also measured the signal particle numbers in the TYAG ceramics. We can find with the increase of ether, the signal particle has been greatly decreased. And from the TM observation, we can find the grain boundary of the TYAG ceramics are very thin and very clear. So we then observed the inline transmittance and also the optical loss of the prepared TYAG ceramics. We can find that the optical loss uh, of of this TYAG ceramics is about 10 times long that of TAG ceramics. By the XPS analysis of this TYAG ceramics, we can almost find no we can almost find any turbine 4 plus ions in such TYAG ceramics. So then we measured the thermal property and also the validity constant of such TYAG ceramics. We can find that 20 atomic percent substitution validity constant reduced by about 24%, and the thermal conductivity reduced by 9.4%. However, this value is still higher than that of TGG's single crystal. So this is another composition optimization strategy by the substitution of schedule. Because the schedule can occupy both terbium and aluminum sites with high consolidation. So the low addition amount means has low impact on the magnetic optical material, and also the thermal property of this kind of material. So using the same strategy, we use the calcination of the powder mixture and the second ball milling process to release the stress during the sintering process. So we can find that the schedule addition can effectively promote the solid state reaction, and also the schedule oxide enlarges the densification activation energies. So these are the figures on the morphologies of the TSAG ceramics with different additions of scandium oxide. So the up part is the ceramics after precintering. In the middle are the samples after heat post-treatment. We can find that with the increase of the scandium oxide content, the signal phase can be effectively suppressed. Without any scandium oxide addition, we can find many aluminum signal phase in the TAG ceramics. However, with the increase of scandium oxide, we can find the number of the scalar phase decrease, and then for example, with percent scanning oxide addition, we can't find any scalar phase in such TSAG ceramics. So we also measured the XRD pattern and the lattice parameter and the theoretical density of TSAG ceramics. We can find that scandium occupies both terbium and aluminum sites. After the scandium substitution, we can find that the ratio of terbium to alumina is less than 0.6. So from the photo of the TSAG ceramics and the inline transmitters code, we can find that scandium oxide introduction can effectively improve the optical quality of such TAG ceramics. We also investigated the XRD pattern of TSE ceramics. It can be concluded that scandium substitution has very little effect on the valence state of terbium. So we measured the validity constant of such 4% addition of scandium TAG ceramics. We can find the validity constant of this material is about 164.4 at the wavelength of 633. So this value is still about 21% higher than pure TGG single crystal, and the thermal conductivity of this TSAG ceramics is about 3.46 watt per meter per K. So this value is equivalent to TSAG single crystal. So then we tested the XRD pattern of the powder mixture, calcined and at different temperature. We can find with the increase of the calcination temperature over 1150 degree, we can't find any terbium for oxygen 7. So and the difference in particle size is small, even at different calcination and temperature. So we also investigated the densification of such TSAG ceramics fabricated by powder mixture and calcined at different temperature. We also measured the morphology of such TAG ceramics with 4% scandium oxide addition. We can find that the powder calcination temperature has very little effect on densification activation energy, and the grain size, the average grain size is only 1.1 micrometer. So this value is much smaller than the sample presented in the vacuum. So this morphology shows the TSAG ceramics after heat post-treatment at 50 degree, we can find that the average grain size is about 1.2 micrometer, and we will find more residual pores in the air pre-sintered ceramics. So, from the photo of the TSAG ceramics, we can find some cracks when the powder calcination temperature is lower than 1100 degrees. And after heat post-treatment at 1700 degrees for 3 hours, we can find that the average grain size of the TSAG ceramics reaches 10 micrometer, and the inline transmittance of the optimal TSAG ceramics is about 79.4% at 1064 nanometer. So then we use vacuum pre-sintering and heat post-treatment to prepare such TSAG ceramics. We can find the average grain size of such TSAG ceramics is as large as 22.1 micrometer. However, the optic transmittance of such TSAG is even high, which are about 82.2% at 1064 nanometer. Even at the wavelength of 433 nanometer, the inline transmittance reaches 81.2%. So here comes the conclusion. First, the first part is on the fabrication and microstructure of TAG ceramics. So by component optimization and phase and thermal analysis of turbine 4 oxygen 7 raw powder were conducted. So the TAG ceramics with thickness of 1.3 millimeter has the inline transmittance of 82.8 at 1070 nanometer, and the thermal induced depolarization reaches as high as 1.2 kilowatt. So this shows that TAG ceramics has superior performance compared with TGG single crystal. The second part is on composition design and optimization of TAG ceramics. To enlarge the solid solution range of TAG ceramics and to suppress the signaling phase, terbium was substituted by yttrium and scandium, respectively, and the effect of the yttrium and scandium on the property of the ceramics was studied. The optic loss of the TYAG ceramics was about 1 order of magnitude smaller than that of TAG ceramics, and the inline transmittance reaches 82.9% at 1064 nanometer. So with 4% scandium addition, the Verdette constant of such TSAG ceramics reaches 164.4 at 633 nanometer, whose inline transmittance reaches 82.2% at 1064 nanometer. So this is the outlook of our research work. So we in the next step, we will further reduce reduce the addition amount of scandium to maintain the high validity content and high thermal conductivity. And also, the second part, we will also optimize the morphology of the powder by adjusting the ball milling process and the assisting actives. The third part is we will further optimize the shipping technology. For example, to prepare the granule powder or use some weight shipping method to obtain even depth and uniform grain body. And the last step, we will prepare some complete magnetic optical ceramics with multi-layer heat dissipation structure, or such magnetic optical ceramics with plate shape. Here is the advertisement, because I am the associate of Journal of Advanced Ceramics. So the impact fact of this journal in 2024 is about 16.6. So which means GCL ranked number 1 in about 33 ceramic journals. So if you find you think your work is good enough, so welcome to submit your papers to Journal of Advanced Ceramics. So thanks for your attention.
Thank you, Professor Lee, for your impressive talk. Unfortunately, we have no time for questions, and we should proceed with next report. Thank you so much once again.
Thank you.
The next report is invited speech, which will be given by Jan Hostasha from Institute of Science and Technology for Ceramics, National Research Council, Faenza, Italy. Jan, please share your screen.
Okay, just a second. Oops, no, that's not the one. My apologies. That should have been working. Why? No. Okay, I guess now it should be fine, but I'm not 100% sure because I think you still see a different slide than I do. Okay, sorry for this.
20 minutes.
Delayed start. Yes. So I hope you can see it well.
Yeah, it's okay.
Thank you. And firstly, I'd like to thanks to the organizers for inviting me, because it's really an honor and I really do appreciate it. It's a pity I can't be there in person, and I hope next time that would be possible. But for the moment, all you have to do with is this online connection. So in this talk, I'd like to say it's going to be a bit more conceptual on transparent ceramic composites and what you can get, where you can actually move in this area that's been studied to a certain extent, but I think that still has not been discussed enough. So the work is based on different parts of work, also on collaborations with our colleagues in the Czech Republic, and also thanks to the work that's been done by our visiting PhD student, Daria Chernomorec, who actually came to our institute from Kharkiv, and also some work with our colleagues from the National Institute of Optics at Sesto Fiorentino in Italy. So the presentation itself is going to be quite straightforward. I'd say a few words on transparent ceramics, although after the keynote before me, I don't think that much needs to be said. And I'll get to the transparent ceramic composites, both in terms of their fabrication and in the use and applications. When we look at transparent inorganic materials for optics and photonics, so okay, let's leave plastics apart. The standard one would be glass, but while glasses are very easy to shape, both in terms of, let's say, of different sizes and shapes, you really have a drawback in terms of material properties, in particular thermal conductivity or mechanical performance. And on the other hand, you have single crystals where, thanks to the pretty much perfect structure, you have really good properties, but they're difficult to produce. When we talk about shaping, it's mostly CNC machining of grown crystals. And you can't also produce every composition that you'd like to because of some, say, inherent limits due to whether it's phase changes or some segregation. And then we have transparent ceramics that come quite, let's say, in the middle, hopefully taking the best from both in terms of having properties that belong to crystalline materials, but at the same time being much more easily shapeable, and also giving us the possibility to create composite structures, and I get to that quite soon. And when you talk to people who work on transparent ceramics, okay, generally you consider transparent ceramics being materials that are crystalline, more specifically polycrystalline, otherwise they'd be single crystals. And they're produced by ceramic processing techniques. So that means usually you start from powders, give them shape, do some thermal treatments, and obtain a dense material. And if you want them to be transparent, then in most cases, you need to have a single phase material because it's difficult to find another phase that would be of the same refractive index. And in most cases, they should be optically isotropic, so that you have cubic crystalline structure and you don't have different values of refractive index in different directions. And that means that in principle, you should have no pores and you should have no secondary phases. And when I get to the title of my presentation, on one side, you have the possibly single phase materials with no secondary phases. And then when you talk about composites, it's usually materials that are composed of at least two different phases, because otherwise it wouldn't be composite. And I understand that this is where the question comes, okay, yeah, this doesn't really seem to be compatible, is it? And as a matter of fact, in the standard cases, it's not, but in some cases it is. And so that's where I want to get. So which kind of composites can be transparent when we talk about ceramics? So as I said, the losses in transparency, or if you want to have material that's transparent, you should reduce losses. And in the case of ceramics, it's mostly scattering on some heterogeneities, which would be usually pores or secondary phases. We can eliminate pores, let's see, from the discussion, because pores are really deleterious, and those would ruin pretty much everything, because the refractive index of a pore is usually around 1, and the difference is just too high, so they scatter a lot. But if we look at the inclusions of secondary phases and take as an example yttrium oxide matrix, where you start adding magnesium oxide inclusions, and you model that for 1 millimeter thickness and the wavelength of light at 1 micron. So the dashed line would be the theoretical transmittance of the material. And if you start adding by very, very little amounts, like this is in volume %, the magnesium oxide inclusions, And on the x-axis, you can see how the effect changes for different size of these inclusions. You can see that when we get to, let's say, 99.9% yttrium, and the rest is magnesium oxide, so very, very little, in the micron size, let's say, there's already quite a significant impact on the inline transmittance. And if you get to 1%, so still not that much for a composite, right? You get to 0 in quite a wide range of inclusion say size. And let's say that the scale that we have down here is pretty much what you'd usually see in ceramics in terms of inclusion size. So this shows that it's not really easy to make these materials transparent. But what we see here is modeled for 1 micron wavelength. If you look at the right-hand side, here we add one more axis, which is the wavelength of light. And you can see that if you increase the wavelength of interest, and if you keep the scatter diameter low, you actually get to a zone where the transparency is pretty good. And this is where you might want to aim for in reaching good. In reaching good transparency. And you can see that the effect doesn't change particularly if you have 10 volume% of magnesium or up to 50% in yttrium. And when we get to the 50-50 case, we also did some more calculations to see how that changes between having magnesium in yttria or yttria in magnesia, and the difference is quite low, so that's quite consistent. And when you look at the more typically shown curves for transmittance, so wavelength dependent, you can see that for, say, 100 nanometers inclusion size, you can get quite nice transmittance in the near infrared, let's say from 2 microns on. And that's actually where you can find really materials that are transparent. And the yttrium oxide, magnesium oxide system was not been chosen by accident, but this one really works because you have a system that's nearly non-miscible, so you really have the 2 separate phases. And it's something that's been proposed already 20 years ago with the idea of reducing grain size of transparent yttria by pinning the grain boundaries with magnesium oxide. But it's been then elaborated more recently in some different works. And I found this illustration, and it shows quite nicely the concept. So if you have long wavelengths of radiation of light, and you have very small grains, then they can actually pass. If you have very small grains, even shorter wavelengths may pass unless you hit a pore. If the grains start to grow big, then you scatter too much and the shorter wavelengths will not pass at all. And if you look at a real case scenario, so that this would be microstructure of such nanocomposite, where you can see that the magnesium oxide grains are quite reasonably distributed within the, well, if you can call it, matrix of yttrium oxide. And if you remember the curves that I've shown for the 1, 2, and 300 nanometers of inclusion size, well, now when we compare it to the real data, we see that the measured curve is somewhere between the 1 and 200 nanometers, and that fits quite nicely with the model that we have and with the grain size that you see in the pictures. So that means that with really just numerical modeling, you can get to model the transparency of these materials quite well. Then more recently, you can also see different systems that have been produced in this direction, and these materials clearly are interesting for inference transmittance, whether it's for highly resistant materials for domes and windows, or maybe even for some photonic applications. And in terms of producing these materials, usually what you need to do is you need to have very small grains, and that means you need to start from very fine powders, and then usually use methods that do not lead to grain growth. And so in general, it's applying high pressures, or also there's some first results on microwave sintering. I'd be interested to see more of that. And we already see that this works. And that would conclude the nano composite part. But then on the other hand, you can say, okay, does it have to always be just that small, you know? Because if you remember the curve at the beginning, the transparency got also better when the inclusions would be very big. And actually, you can have macro composites. It's just not always people tend to call them like that. But for example, Professor Zhang Li actually did have some of that towards the end of his presentation as idea what to do, because what you want in these composites is not usually to have better mechanical properties, but to have more functionalities. So for example, when you use cladding, when you use multi-layer structures, those can be actually considered transparent macro composites. And what that means that often by adding, for example, a dopant, you have a drop in thermal conductivity of the different materials. And that's normal and expected in the oxides. But what you can do is you can make a multi-layer structure that would then help you distribute more evenly the temperature during laser operation, for example, in this case. And that would also allow you to have parts that are not heated during the laser operation. And that's something that's been successfully tested and used. And okay, in most cases, you might have also some slight interdiffusion zone, but still you have two parts that are quite well defined by their distinct material properties. And if you take that even a bit further, what you can do with ceramics, but you probably can't do with single crystals, for example, is to make waveguide structures where you tune the composition of a layer or even a ribbon, let's say, within the material that changes the refractive index. And if you do that by adding also laser dopant, then you can have a laser waveguide where the light is guided directly through the active medium. And around that, you have a part that's not absorbing the pump, and that helps you reduce the thermal gradients. And that was something that we tested, and it worked quite nicely. Also in terms of cooling that down. So eventually you might get to the direction of fiber-like structures, but with let's say with a ceramic microstructure. And then another example is that of having some absorbing parts. So whether it's absorbing cladding, where you remove the spontaneous emission photons, or for example, in the case of saturable absorbers, when you need to then create some high power pulses. And another example that I think is interesting is the possibility to produce composite ceramics for scintillators, where you manage to analyze or detect different types of rays or irradiation within a single device. And here again, if we want to get to how you make these, it's a bit more straightforward if you start from bonding, because that's how you can make these structures even from a single crystal. The limitation is, of course, in the shape of the interface, because you need to have very, very high, let's say, high grade polishing, and it's quite demanding also economically. What you can do in ceramics is to co-sinter, so you pre-sinter your parts, then you put them together, and you do the final sintering step by actually bonding these parts. And that already helps a lot, because you have less limitations on the surface quality, and also the machining is easier. And that's where I would say the advantages of ceramic processing start. But then you have a load of different options that can also go beyond that. The standard one would be pressing, where you press one part, then you press another. Here there was quite a nice idea from the people from the Lawrence Livermore that 3D printed one part that was, let's see, coupled shape, and then they pressed this part into the powder to have a defined dopant distribution gradient. Another would be tape casting, which is particularly useful for the layered structure. So for example, the waveguides, or in general, anything where you have multi-layers. you can go towards slip casting, and that's maybe a bit more limiting on the effect of the specific shape, but you can more easily obtain also relatively large components by that, especially if you use pressure slip casting like the group of Rémy Boulay-Stakes in Limoges. And you can get to additive manufacturing, and that's been really interesting in the last years, because the different approaches allow you really to deposit, let's say, the different compositions into different parts of the material as you want, and you can design that quite nicely. So I expect to see more of that in the upcoming years. But so far, this was useful for the materials that are quite similar, because you can then sinter them in the same way. If that's not the case, then you have to use some, let's say, different approaches. And this is also, in terms of bonding, it's easier, and you can use that, for example, to bond together materials like spinel with YAG or sapphire with YAG to have some heat sinks. You can do optical bonding, but that's really demanding on the quality of the surface. So it's really nice, but it's a lot of work. Or you can use, let's say, some less maybe you can use technique that in a certain way would fit all the materials that you use. And this is the example of the scintillator that I was talking about, where you have YAG and another garnet that has some issues under vacuum, because when you want to produce YAG, you usually use vacuum sintering. When you want to produce gallium, gadolinium, aluminum garnet, you can't use vacuum sintering because you would have gallium leaving your material. But what you can do is to find a way that allows you to sinter them both to transparency. And that's what we did after some experimenting. When we pre-sintered the material in air and then hipped it, the transparency was pretty nice, and we could actually have parts that were composed of the two different components. So eventually you can also try to tune the process to obtain more dissimilar macro composites that are still transparent. And so to conclude my talk, I want to say that it's important that composites are considered not just as, okay, CMCs, materials where you increase the mechanical properties, but also as very interesting optically transparent materials, whether it's in the nanocomposite range, where you work probably in the infrared, and I still do expect some more, let's say, mixtures of compositions here, also because probably for the inclusions, you do not necessarily have to have cubic materials. On the other hand, you can have the macro composites, where it's really about the functionality and putting together parts that give you advantage or better performance of the whole component that you produce. And here I really expect to see more to come from the additive manufacturing side. And also, I mean, I have to say I saw some really nice results from Shanghai coming in the past year. So I expect that be also something we might hear of quite soon. And with this, I would like to thank you all for your attention and for listening to me. It's been a pleasure. And I don't know if we have time for questions. If yes, then I'm ready to answer them.
Thank you. We have time for one little question, please. No questions. Okay, let's send Jan Hastasha again. Thank you very much. And we proceed with our talk. Alexei Kapustnik from Institute for Single Crystals, binary and ternary optical crystals, zinc selenide and zinc magnesium selenide, doped by science for mid-infrared applications. Please, up to 10 minutes, please.
Okay. Good day. I want to present you my speech about binary zinc selenide crystals and substitution solid solution zinc magnesium selenide doped with iron impurity for mid-infrared applications. But first of all, I want to give you a little bit more information about non-doped crystals. It's a well-known crystals like tungsten that is used for production windows, lenses, and prisms and other elements of passive optics. It's a well-known fact that doping with transition metal impurities of A to B6 halcogenate materials allows to create an active materials for lasing in mid-infrared region. In this work, we have grown two such materials. It's a zinc selenide and more specific substitution solid solution, zinc magnesium selenide doped with ferrum impurity. For this, we have used setup that was manufactured inside the Institute for Single Crystals in Ukraine. All characteristics of such setup you can see on this slide, and this setup uses vertical Bridgman method under the extensive pressure of the inert gas. About the structure of these materials, zinc selenide is characterized by the cubic sphalerite structure, and the substitution solid solution zinc magnesium selenide can be characterized as with the cubic structure, as also it can be hexagonal wordsit structure depending on the manganese concentration inside. Also, you can see the samples of the grown ingots, and all samples have the concentration of impurity around 5 by 10 in degree 18 ions in 1 cubic centimeter. Also, we checked the composition of the ground crystals. Here you can see elements distribution inside the volume of the ground crystals. You can see that magnesium and zinc substituted each other well, and the magnesium concentration decreases from the top to heel of the ground crystals. At the right side, you can see the unit Kel parameters A and C, depending by the magnesium concentration. As you can see, such dependence is non-linear. Dependence of the energy band gap of these crystals is mostly linear, and also with increasing of the concentration of magnesium, the splitting between the energy of the ion levels decreases in such relation. Because of this, we can see the effect of the redshift of the absorption and emission bands of the active ions for these materials. At the left side, you can see such absorption band for zinc selenide crystals doped with iron impurity. Because of zinc structure, there is a multiplied number of extremes. At the right side, you can see this effect, the effect of the shift to the more longer wavelength region with the manganese concentration increasing. We measured a lot of samples, and this slide provides already a statistic of all these measurements. This data helps us to predict the position of the emission band and the luminescence band and the absorption band of the active ions inside this substitution solid solution zinc magnesium selenide. This is very needed for specific applications. Next slide shows the very big difference in luminescence position spectra for between the zinc selenide doped with ferrum and zinc magnesium selenide. So what I want to conclude, the obtained crystalline materials are highly promising for operation in the near middle infrared region. The correlations between the changes in the zinc magnesium selenide ferrum solid solution composition and the structural and electronic properties, as well as the maximum position of the ferrum ion absorption emission spectra were considered. The redshift of the Young-Taylor components of the total absorption spectrum was shown, and the obtained results can be used to predict the lasing range for this material. And also for our future work, we can make some optimizations of the bond concentration, optimization of growth regime to obtain crystal with a minimum number of defects. And in the future, we want to make a scaling up to have a more larger crystal sizes. Thank you very much for your attention.
Thank you, Alexei. It's time for discussion. The question, please.
Hello.
Hello.
Thank you very much for your nice talk. How about the optical quality of the complete single crystal?
Optical quality of the single crystal?
Yeah.
Yeah. So optical quality of the obtained crystals are actually not bad. All crystals that we have grown, they contained large blocks. And transparency, for example, for zinc selenide crystals is around almost 70% in the middle infrared region. For the zinc magnesium selenide, also almost the same, a little lower, but transparency is very good. Theoretical level of transparency for zinc selenide, it's almost 70%.
So, did you ever test the optical loss of the compound single crystal?
Compound. Composite?
Solid solution.
Solution.
Yeah. We have a doped solid solution. It's a triple crystal substitution solid solution, and the doping we are performing while we performing the growth process. So we add in impurity inside the raw materials.
What about optical losses?
Optical losses. Optical losses, it's a very good question, but it depends on the quality of the matrix itself. The ferrum, if the quantity of ferrum is not big, it doesn't affect on losses.
So you didn't measure the optical loss of the solution.
Optical losses of the solution. I will try to show. Sorry. Here you can see the data for doped solid solution with 2 ions actually. And it's a concentration losses with the temperature. You can see the intensity and losses by increasing the temperature, and it's only this we can provide about
So what's
losses.
the meaning of intensity? So what's the meaning of intensity?
Luminance. It's luminescence.
Yeah, it's
Oh, okay.
luminescence
Oh, okay,
intensity,
it's the
yes.
luminance. So yeah,
Yeah.
I mentioned the optical loss. Maybe the optical transparency of the solution is a little bit lower than the zinc selenide single crystal. So
Yeah, it can be compared, yes. It's
okay, I know. Thank you.
I have also small questions. Alexei, what can you say about distribution of main components within the crystal? And maybe there is some way to increase the homogeneity of distribution.
Yeah.
For the solution, I know that starting charge may be prepared from different composition. Have you used such approach to increase the homogeneity of activators and
Okay, thank you very much for your question, Roman. Yes, there is a way to make it a better contribution of every element through the length of the ingot. You can use charging of raw materials depending of its density and melting points, and step by step providing the raw materials inside the crucible, you can have, as a result, more homogeneous ingot. But actually, for these materials, we did not use this approach, but such approach exists. I know about it, and maybe we will try it in the nearest future.
Okay, thank you. Any other questions?
Yeah, we have one question in chat.
Oh, okay. So what method did you use to measure element composition on slide 5?
It's a electron microscopic element.
It is.
It is, yes.
Okay. So thank you again for your nice talk.
Thank you very much.
Now we are going next report. Ilarion Ramil from the Institute of Scintillation Materials. The report title is Some Features of Composite Scintillation Material based on small size grains of organic single crystals. Please, Ilarion, share your screen.
Yeah, I'm sharing it now. Oh, can you see it?
Not yet.
Okay, is it loading? Hello?
Now it's okay.
It's okay? Right. So basically, hello everyone. My name is Ilarion Ramil, Institute for Scintillation Materials. And today we'll be talking about the modern type of scintillation materials, namely organic composite scintillators that consist of microscopic grains. So what are scintillation materials in general? They are materials capable of converting the energy of ionizing radiation into visible light, into near UV light and near infrared. As a result, they have found widespread use in all industries where ionizing radiation is either directly used or can be generated. Scintillation materials have several key parameters. It is their light yield, which determines the number of photons of light generated by the scintillator per unit of ionizing radiation energy. This is their luminescence decay time, which determines the time from the onset of the to the end of the scintillator's light pulse when it's struck by a single ionizing particle or quantum. This is so-called discrimination capability, which determines the dependence of the, let's say, glow dynamics of a single light pulse on the type of ionizing radiation. And it is this is radiation resistance, which determines the scintillator's ability to continue performing its primary function, that is emitting light when irradiated, under high fluxes of ionizing radiation. Scintillators can be divided into two main groups based on their chemical composition, namely inorganic and organic scintillators. Today we'll stop on organic ones. These substances are top of the line in 3 of the 4 parameters listed above. They have a high light yield, 10,000 of photons per mega electron volt, MeV, enabling accurate detection of even low energy radiation. They have very short decay time, allowing them to be, so to speak, ready for the next particle or quantum in a matter of nanoseconds, basically. And they also offer the most accurate determination of the type of ionizing radiation they detect, thanks to their high hydrogen content. Their only drawback is relatively low radiation hardness, amounting to a few megarads. Nowadays, the issue of separate detection of ionizing radiation has become quite popular. There are a lot of situations that require determining which radiation is being detected. Indeed, it is important to remember that alpha particles and fast neutrons are 20 times more harmful to humans than gamma radiation. Therefore, determining the radiation field in which we are located is truly vital. At the same time, applications such as environmental monitoring, border control, or recording of rare interaction events require large detection surfaces. But organic scintillators come in the form of single crystals, liquid scintillators, and plastics and so-called heterostructured scintillators. That the scintillators are consistent of individual microcrystals, single crystals, that are interconnected by somehow. For large volume applications, the use of organic scintillators in their single crystal form is too costly. Liquid scintillators, in turn, are manufactured primarily from the flammable materials. Plastic scintillators have low discrimination capability due to their polymer structure. Therefore, composite scintillators are, as a type of heterostructured scintillators consisting of single crystal grains bound together by a transparent gel matrix, are optimal for such applications. Recently, my team and I were able to calculate and demonstrate that small grains of organic scintillators, when properly sized, can distinguish the desired type of ionizing radiation several times more accurate. This is possible because of triplet excitons can undergo processes similar to their reflection from the surface of the single crystal. Basically, any single crystal and single crystal grains all through. Generally speaking, when an organic scintillator is irradiated with ionizing radiation, states such as singlets and triplets are generated. The ratio of their numbers depends strongly on the type of ionizing radiation that hit our scintillator. Namely, the energy loss of this radiation per unit path in the scintillator. Singlet excitons are responsible for the direct S1-S0 transition, which produces luminescence, while triplet excitons are unable to independently produce luminescence due to their low energy frequency. Their emission is possible only when two excitons as we can see from this formula, meet together and recombine, which creates energy sufficient for S1 S0 transition. So, therefore, in a scintillation pulse, the initial part, the so-called fast component, this is this part of the scintillation pulse, is caused by direct singlet-singlet transition, while the slow part, let's say this part, caused by the same transition but formed by the fusion of triplet excitons, and that needs time. So, excitons are mobile quasi-particles. Their motion determined by the interaction of individual scintillator molecules. Therefore, excitons are capable of leaving their point of origin. While singlet excitons emit their light on their own, triplet excitons can lose their energy without emission, undergoing so-called monomolecular quenching. This is also often depicted by the beta. If they do not find the pair without their lifetime, they undergo this monomolecular quenching. Such excitons can travel significant distances due to their long-term lifetime and high diffusion coefficient in organic scintillators. This is lifetime, this is diffusion coefficient, basically they're quite high, and for our organic scintillators, the LT, the travel light distance, can reach several micrometers, so tens of micrometers. So, therefore, to increase the number of triplet excitons, triplet exciton interactions, basically, we propose to use those excitons in single crystals and very large grain leave their point of origin, diffuse into the bulk of the scintillator material, and lose their energy without emission. However, quite small grains have often been optimal, resulting in detector based on them being very opaque. This confirms the importance of the development and creation of detectors that allow light to escape the scintillation zone and reach the recording electronics, basically any used photodetectors. And we have found such a solution. It involves creating multi-layer assemblies containing alternately connected scintillation and transparent layers, creating multi-layer assemblies. Light generated in the composite layer can propagate in 4p geometry, that is, in all directions from the point of emergence. Therefore, some portion of the light can escape from our composite scintillators and enter the transparent layer. Through the propagation of the light in the transparent layers, prevent it from being lost within the composite scintillators itself, and would happen in a classical design of pure composite detectors without such a transparent layers. To reduce the number of variables, we chose transited beam as a popular organic scintillator and the scintillator raw material. We selected grains in the 0.3-0.5 millimeter size range and used them to fabricate 1 millimeter thick composite layers, each layer measuring 10 by 10 millimeters. Silgard 184 polydimethyl siloxane was used as the matrix, and it was also used to create such transparent layers. As a comparison sample, we created a composite detector made of the same compound as the multi-layer composite layers and with the same height as the proposed multi-layer design. A study of the light output showed that in harsh cases of light generation using alpha particles, that is when scintillation occurs in the top of the construction in the most distant region from our photodetector, it allows us for a light output more than three times higher than for our conventional scintillators, composite scintillators, basically. This became possible because a significantly larger number of photons generated in the scintillation pulse are now able to avoid dissipation in our composite scintillation materials, instead hitting the photodetector and being detected. However, we can see that the number of pulses, number of events basically detected over the same time has decreased significantly. In this case, for a regular composite scintillator, the accumulation time was 600 seconds, and for our multi-layer design, it was 6 times more. So this is because of fewer alpha particles which were used to simulate the harsh operation condition of our scintillator were able to produce a light pulse because they hit a transparent layer and do not trigger a light pulse. So, to the main conclusions, the proposed design is able to produce the light output that is several times higher than for regular organic composite scintillators. This is possible due to the transparent zones in such multi-layer design. But also, at the same time, the amount of pulses is several times lower due to the lower registration area. That's all for today. Thank you very much.
Thank you, Larion. It's time for discussion. The question, please. I have one question. What can you say about microstructure of your polycrystalline organic material? Have you observed grains, grain size, pores, or grain boundaries, something like that?
So basically, we made some like microscope photos of such composite scintillators to basically verify the grain sizes that are used for these layers. And we actually verified that grains were between 0.3 and 0.5 millimeters. So our sieves used to like separate this grain size, grain fraction, we were working correctly. And also we basically haven't seen any like bubbles or such stuff due to in the production of this composite layers. In the course of the production of this composite layers, we basically used vacuuming of this like compound to basically prevent the incorporation of the like bubbles and so on.
Have you observed the scintillation quenching at grain boundaries? What can you say about quenching processes?
So about processes of quenching, let's eliminate this one. So previous part of our work was to basically prove that this inflation is actually possible. For this, we created a series of different materials with different grain sizes, and for transtile beam used in this particular case, in this particular work, for paraterphenyl and anthracene as the most popular organic scintillators, we observed the following. When particles with average grain size of 60 micrometers were irradiated with alpha particles of plutonium-239 were radiated, their relative light output was like spiking basically. And according to our calculations, the like ratio between the volume of our grain and between the this actually this troll range was optimal basically for this 60 micron grains. So this has proved that the reflection produced such a condition as in this form. So even quenching of the surface wasn't sufficient enough to like downgrade the reflection effect.
Thank you. Any questions? No questions. Thanks, Ilarion, again.
Yeah, thank you for your attention.
Yeah, and we are going to let's talk before the coffee break. Dmytro Stepanenko from Iron and Steel Institute, named after Nekrasov, will present his report, Fundamental Principles of the Temperature Dependence of Viscosity and Electrical Conductivity in Studying the Structural Stage of Slug Metals. Dmytro, please share your screen.
Okay. You can see my presentation.
Yeah.
It's okay. Thank you for the introduction. Hello, everyone. I'm going to present my report on the topic of fundamental principles of the temperature dependence of viscosity and electrical conductivity in studying the structural state of slag melts. So, when discussion slug structure, we use the terms cation and anion because these are general considered the basic structural particles. However, real slag melts have a complex structure, and the concept of cation and anion are insufficient. It is known that the properties of slag melts depend on their chemical composition, temperature, and structure. Interpreting the structure of slag melts through their properties is difficult and requires the development of additional methods. Today, there is a lot of experimental data on the properties of slag melts, such as viscosity, electrical conductivity, density, thermal conductivity, and others. The institute, our institute, has created a database called SLAG to store and manage such data. The database contains text information about the data source and experimental methodology, as well as numerical information about the properties of specific slags. Viscosity and electrical conductivity are examples of structure sensitive properties whose temperature dependence is exponential. To describe the dependence, Frenkel proposed equations similar to the Arrhenius equation. These equations are valid provided that the activation energies are independent of temperature and equal to a constant. However, real slags divide from the Arrhenius continuum where the activation energy is constant and independent of temperature. This indicates a change in the structure of the slag melt with temperature. The segment linear regression method was used for a detailed analysis of the temperature dependence of viscosity and electrical conductivity. The basic idea of the method is to divide the range of experimental viscosity and conductivity temperature dependence into several segments and fit separate linear regression models to each segment. The methodological aspects of solving these problems are described in detail in various articles. Segmentation of experimental data made it possible to find temperature ranges at which the activation energies of viscosity and electrical conductivity are constant. The temperatures obtained using this method, you can see dashed lines, we are compared with the results of thermodynamic calculation of changes in the slag's phases composition by FoxH software version 7.2 and experimental measurement of aggregation transformation temperature. You can see solid lines. The analysis results confirm the physical validity of the method, which can be used to estimate liquid and solid temperatures for multi-component slags. The method was used to select the optimal slag composition for the electro slag remelting process. The chemical composition and properties of the slag are presented on this slide. The temperatures of the structure state changes T1 and T2, along with the interval between them. We are determined based on experimental data on the viscosity and electrical conductivity of electroslag remelting slags. Their results show that the slag number 1 is promising to facilitate the smooth ingot surface formation in short collar mold electroslag remelting process due to providing the suitably low values of phase transition temperatures and the wide range between them. The obtained research results show that the adaptive segment regression method can be used to estimate the liquid and solid temperatures for oxide and slag melts based on the temperatures dependence of viscosity and electrical conductivity. This is the end of my presentation. Thank you for your attention. Maybe some has questions.
Thank you, Dmitro. It's time for discussions. Colleagues, please ask the questions. Any questions? I can translate. Okay. Okay. Do you can you say about effect of formation of complex compound during your modeling?
Sorry, but
Do during modeling, are you considering possible formation of complex compounds or of silicates or other compounds in your system?
yes, of course. Yes, this method can be used for other oxide system.
Any other questions? Okay, no other questions. We will thanks Dmytro Stepanenko again. And now it's time for a small coffee break. We will return to the session at 11:30, and coffee break is in the front of in the hall of our conference room. Thank you. Okay. Remy, are you here? Remy Ballistics, are you here? Do you hear me?
Yes,
Yes, yes.
I'm connected and I hear you.
Okay. Are you ready to make report alone? Now at 11:30, we can change. We have to change your report and report by Jan Sean.
Mhm.
It's okay for you?
So I have to start now?
Yeah, in 2 minutes. Are
No,
you ready?
okay. Yeah.
Are you-
Yes, it's okay. It's okay for me. No
Yeah,
problem.
thank you, thank you. So we'll proceed with your report now. Okay. Change. We change your report and report by Jan Sean.
So I
In 2 minutes. Okay. Okay, colleagues, it's time to proceed with our morning session. There will be some changes in our program. The next talk will be given by Rex from University of Limoges, France. The title of the talk is Role of the Fluorine on the Elaboration and Optical Properties of Yttrium Oxide Ceramics doped by Holmium Transparent Ceramics. Since it's invited speech, you have up to 20 minutes. Please share your screen.
Can you see my screen or?
Yeah, but not full screen yet.
Is it okay now?
No, just a moment. Maybe we should wait. Still not full screen. Oh, yeah, it's okay.
Okay now?
Yeah.
Okay, perfect. Don't hesitate to stop me if there is any problem. So thank you for invitation. It's a pleasure for me to present a part of my work at the Institute for Research on Ceramics in Limoges in France. And today, I will present you some of our work on holmium doped yttria transparent ceramics. So we work in our lab on various transparent ceramics for different applications, especially scintillators, lasers like amplifier media, site-variable absorbers, or Faraday rotators, for example. So if I just have a look on the story of transparent ceramics for laser applications, it's a pretty long story now, and we can see that so the various shapes and compositions were developed over years, and we can see still now that there is still limited size and quality especially for fluorides and sesquioxide ceramics. And also Konoshima Ceramics is always the leader in this area, and that means there is some research work to do to better understand different process parameters, for example, that could improve the laser efficiency of such ceramics. So if we have a look on some properties of the main transparent ceramics that could be developed, so you can find fluorides, garnet, sesquioxides, tungstate, fluoroapatites, and the ceramics, the composition of sesquioxides has the best thermal conductivity and is very well suitable for high power laser applications due to heating, a better heat release during the laser operation. Nevertheless, if you have a look on the structure and especially the melting temperature of such sesquioxides, they melt at very high temperatures, so it's very difficult to manufacture this kind of material in the form of single crystals because it needs very high temperatures for long times, and so the size is limited and the quality is limited also, and this is why it's very interested to address to see different processes to make this kind of materials, and especially the ceramic one is very well adapted for the fabrication of this kind of material. And for now, there is various techniques used for the ceramic processes, especially non-conventional sintering. So this is the first way to sinter to perfect density this kind of material. So you can see on the left, for example, the first way is the classical shaping and then natural sintering under air, oxygen, or vacuum. This could lead to transparent ceramics. Eventually, you can apply also a final stage of hot isostatic pressing in order to promote the densification of residual porosity. And two other ways: you start directly from the powders, and you can use hot pressing and spark plasma sintering. So thanks to these different ways, it was different compositions of sesquioxides were successfully obtained with various optical qualities, and only few of them has led to a good laser operation. That means all of the steps of this process should be perfectly managed and optimized in order to obtain very high optical quality ceramics. The second way to obtain perfectly transparent and dense ceramics is to use sintering additives. So for sesquioxides, we have classically zirconium oxide, lanthanum oxide, or fluorides that are added to the initial composition in a few contents in order to promote densification and porosity elimination. And especially on fluorides, the effect is pretty complex because it can melt, evaporate, interact with residual carbon, and so on. And there is many studies on this kind of topic in order to better understand the role of this kind of fluorides. In this case, today I just want to address the effect of fluorine itself because it's not really well known. So we have performed some studies on fluorine. So this is the outline of my talk. So first we have studied the reactivity of the yttrium oxide and yttrium fluoride system. We have studied the natural sintering behavior of this system, and then we have applied non-conventional sintering technique, especially SPS and orthostatic pressing to this kind of ceramics. And finally, we have some conclusions on the optical properties of this kind of ceramics. So first, if we have a look on the yttrium oxide, yttrium fluoride system, so on the right, you have the phase diagram showing a solid solution for a limited content of fluoride inside the matrix of yttrium oxide. And so to get this kind of material, we just put yttrium oxide nanopowder and we mix with various amounts, limited amounts of yttrium fluoride. We press the powders and then we have made some thermal treatments and corresponding analysis. So we expect that yttrium fluoride during the thermal treatment will react and enter inside the yttrium oxide matrix, but we have first to verify this point. So we have verified that we form a solid solution by XRD after a thermal treatment at 1700 degrees under air. And when we increase the amount of yttrium fluoride, we have a shift of the main peaks of the diffraction peaks. And after refinement, we can obtain the lattice parameter. And so we can see that there is a linear variation of the lattice parameter as a function of yttrium fluoride. That means that fluorine should enter in solid solution with the formation of this kind of material. So we have the substitution of part of the oxygen by fluorine, and we have the formation also of vacancies. So this is concerning the structure. So we have a good reaction between these two powders, and we have the composition we expect, but we wonder now the reaction mechanism during natural sintering. So we have performed the electrometric analysis under air of pure yttria and yttria doped with yttrium fluoride, and we can see almost similar behavior. This is not it was not really expected, but the behavior is very similar for this kind of amount of yttrium fluoride. So the effect is very limited during sintering on densification. But we can see mainly two differences. The first one is around the temperature melting of yttrium fluoride. Here we have variation of the densification rate here. That means during the melting, there should be some effects on the densification of yttria. The second point is that after this temperature, we have a significant difference in the densification rate, and the temperature for the maximum rate of densification is shifted to higher temperatures of about 50 to 80 degrees. So that means we have significant effect on densification that is not too high, but it's still significant. So this is the first point, and we have tried to better understand the effect of yttrium fluoride during the densification, and so we have stopped at 1400 degrees the thermal treatment. That means at a temperature where we observe the maximum rate of densification, and we have performed TEM observations. So we can see 2 grains here of yttrium oxide, so the size has increased, from the initial powder. It's well crystallized, it's cubic yttrium oxide, and we can see at the surface here a layer of about 5 to 10 nanometers in thickness. And thanks to selected area diffraction here, patterns here, we can see that this layer is polycrystalline. So this is the first point. And the second point is that we have identified two phases that are Vernier phases at the grain surface. So the diffraction points here corresponds to the two of these phases. And these phases are present in the phase diagram, and they are Vernier phases. So that means that yttrium fluoride during the increase of temperature reacts with yttrium oxide and form here yttrium oxyfluoride phase in the form of a thin layer at yttria particle surface. And so we can expect that for higher temperatures, the fluorine enters inside the yttrium oxide matrix and form the solid solution as evidenced by XRD. So if we have a look on ceramics during the thermal treatment, during sintering, at final stage of sintering, so for temperatures higher than 1400 degrees, we can see first for pure yttria that we have classical sintering. We have small grains at intermediate temperature with residual porosity. And for higher temperatures, we have almost dense microstructure, bigger grains, some residual porosity that is at intergranular or intragranular also. So this is for pure yttria. When we increase the amount of yttrium fluoride, we can see that we have bigger grains. So that means fluorine increases the grain growth during sintering. We still have similar porosity, and we still have also intragranular porosity. And one result is that for the higher temperatures and higher amounts of yttrium fluoride, we have very, very big grain growth during sintering, and that is accompanied with the formation of a lot of intragranular porosity due to the separation between pores and grain boundaries. So that means yttrium fluoride increases grain growth, and it does not seem to promote so much densification. And we can summarize these two results on the sintering map. We have put here the grains diameter as a function of the relative density for various amounts of yttrium fluoride. And we can see that we have different trajectories. So this is in blue for the pure yttria, here and here when we increase the yttrium fluoride. And in any case, at the end of densification, at the end of sintering, the curves go into the separation domain between pores and grain boundaries. And what we can see also is that for the higher amount of yttrium fluoride, we have an increase of grain size compared to densification. And we have also a decreasing of the densification rate for the same temperature. So that means during natural sintering of yttrium oxide under air, fluorine is not adapted to obtain perfectly dense and transparent ceramics. So now we have tried to obtain transparent ceramics, and we have applied, the second way is to apply pressure during sintering. So we have used two different equipments. So the first one is spark mass sintering. So we put the powders inside the graphite die, and we apply a pressure, and we apply also a strong current passing through the matrix, and so heating the matrix thanks to Joule effect. And the advantage is that we can reach very high sintering rates, very high temperatures in a reduced time. And thanks to this equipment, we can obtain different SSK oxides The process is very short, so it takes less than 1 hour from cold to cold to obtain a transparent ceramics. And thanks to the very high sintering rate, we have a very limited grain growth during sintering. So we can obtain transparent ceramics with a very small grain size. Now we were wondering the effect of fluorine doping during this process. The second process is hot isostatic pressing. So we shape the powder, we make a pre-sintering step in order to obtain a relative density higher than 95%. And then we apply post-sintering, post-densification by hot isostatic pressing. We apply a pressure of gas that is isostatic, and this could remain the residual porosity. One thing is that for a good post-heap, you have to start with the small grains and only intergranular porosity. If you have intragranular porosity, you could not eliminate it during post-heap. So we have to take care here to the initial microstructure we obtain after pre-sintering. Just to put an example, so our post-sintering by hot isostatic pressing is a very well suitable technique to obtain transparent ceramics. You increase the densification rate thanks to the pressure at limited temperature, so you obtain in the same manner than SPS, you obtain a small grain size, and you can totally densify your material. We have demonstrated a few years ago that we can obtain equivalent laser properties than single crystals, and we can obtain more than 100 millijoule class solid-state laser thanks to this technique. So here also we wonder for the effect of fluorine doping during this kind of process. So if we have a look on the samples after SPS or after HIP, the effect of fluorine is not so visible on these pictures. But if we have a look on the SEM pictures here, we can see that fluorine increases also the grain growth during this kind of process. And so we have a pretty big grain size after HIP with the higher amount of yttrium fluoride. So we can observe that the increasing is almost by a factor of 3 when we use fluorine compared to pure yttria in both cases for both of the sintering techniques. And finally, if we have a look at the transmittance, all of these ceramics after sintering, so we can see the lines here for holmium ion that it's normal, and we can see also, especially for the samples used sintered by SPS, we can see the presence here of absorption bands of OH groups and carbonate group also. These bands are not visible on the HIPed samples. That means these kind of impurities are well eliminated, mainly during the pre-sintering step. And SPS is not very well suitable to eliminate this kind of impurities because the schedule is too fast. So maybe we have to decrease the thermomechanical rate, the heating rate during the SPS to avoid these bands. And we can see with fluorine here, we have a small decrease of these bands. That means maybe fluorine can help to prevent this contamination during sintering. So this has still to be optimized, but we have interesting results with a pretty high optical quality for fluorine-doped samples obtained by HIP. Finally, we had a look on the spectroscopic properties of this kind of ceramics. There is no significant effect of fluorine doping after SPS or HIP treatments. We have very, very similar spectroscopic properties. The only difference we have put in evidence is concerning the fluorescence lifetime at 2 micrometers that we want for laser operation. Here, the fluorescence lifetime is higher for the sample obtained by HIP, and it's very, very close to a single crystal fiber. And we suppose that this result is due to the higher grain size for these samples, and that means we have a higher crystallinity for this sample, and so we go closer to the single crystal behavior for this sample. So that it's very interesting, and so we still have to optimize, but we could imagine that we could have laser operation with this kind of ceramics. So as a conclusion, I've shown that it's possible to manufacture rare sexy oxides of transparent ceramics for lasers. We could obtain high doping rates, easy doping also with luminescent elements. We can obtain samples with small or large size, and it's also highly scalable and adaptable to other compositions. Here you have some examples. And the effect of fluorine doping on sintering, we have the formation of intermediate Vernier phase, and so it promotes grain growth, whatever the sintering techniques. And there is a limited effect on densification, especially for natural sintering, and also on optical properties. So it's a good way maybe to improve the optical quality without having some troubles on the spectroscopic properties. So in perspectives, we have still to increase the optical quality and to do laser tests, and also to do bigger samples. So thank you for your attention. I'm open for questions. Thank you.
Thank you, Remy. Colleagues, please, your questions. One question is how you control the fluorine concentration in ceramics.
At the end of sintering, maybe part of fluorine can evaporate. At this moment, we don't have suitable technique to measure properly this fluorine content. We didn't verify the fluorine content. Some chemical analyses are under investigation to verify that we have the suitable content of fluorine after sintering. But we know that we have seen fluorine because of the grain growth and because of the XRD shift.
Thank you.
Yeah, Remy.
Okay,
Thank you very much for your nice talk. I have one question. I found the optical quality of the holding doped ceramics is a little bit lower than the sample prepared by HIP post-treatment. So how do you think, what's the main reason?
What's the main, sorry?
I think, so why? That's why.
Why? So maybe you refer to this results. During post-HIP and with pre-sintering, we take time. We take time to eliminate the impurities. We take time for the microstructure to be more homogeneous and so on. So we could get better result after. For SPS, we only apply the pressure and the temperature in a very short time. And at limited temperatures also, you didn't activate the mechanisms for diffusion, also for volatilization, evaporation of impurities, and so on. So it's too fast, I think.
So, maybe one reason is because of the contamination from carbon.
The initial powders contain hydroxides and carbonates, and I think that these impurities are embedded inside the matrix during the sintering, on the contrary to heap treatment. So I think it comes from the initial powders. We have to clean the powders before sintering.
Yeah. I think maybe another reason is they are very small amount of very small pores in the sample by SPS. Maybe this is another reason. The second reason is because with the pressure, there should be some stress in the ceramics. So stress will also cause birefringence. So this is another reason, I think.
Okay. I don't know if there is any birefringence induced by stress, because we anneal the sample under air after SPS. We anneal at a temperature around 1000 degrees for several hours. So I think that we should decrease the stress during annealing.
So I think there should be some difference before and after annealing on the microstructure. There should be some expansion of the macropores. Maybe it's possible.
Yeah, maybe. Yes, we often observe that we can lose the transparency if we go too high during annealing. Yes,
Yeah.
you know.
But even at the temperature of 1000, I think there should be some slightly expansion, I think.
Yes, maybe it's almost the limit.
Okay, thank you.
Thank you.
I also have small questions. Have you measured your spectroscopic properties at room temperature or at helium temperature?
So it was at the room temperature, and our partners from CMAP have made many analysis, and I don't remember if they have done some analysis at in cryogenic conditions. I think almost of our analysis were at room temperature.
Okay, maybe if you perform analysis at lower temperature, some specific features of the spectra will appear. Maybe some fluorine in some way influences properties of Hornium 3+.
Okay, thank you for advice.
Thank you very much for your nice talk.
I'm sorry, we have a question.
Oh, yeah, of course, please.
Thanks.
Kiev, Ukraine. I want to thank you for the nice presentation. And my question is a little bit philosophical or fundamental. Why do you think yttrium is so productive? Why it works so good in different fields of material science? Thank you.
I don't know really. I only work on this material at this moment for optical applications. I think for different reasons, because the cost is not so high for Ethereum. We can work pretty easily in France on this kind of material because we have a very good industrial manufacturer of rare earth oxides also in France, as you know. So we can do good research on this kind of rare earth oxides thanks to these powders. And the physical and optical properties are also interesting.
Thank you. Thank you.
Thank you.
Are there any questions? No. Okay. Thank you, Remy.
Okay,
And
thank you.
we will proceed with next talk, invited speech by Yannick Schoen from Carl Zeiss Oberkochen, Germany. The title of the speech is Developing Optics Processes for Next Generation EUV Lithography Systems. Yannick, please share your screen.
Thank you very much. You should be able to see the screen now, right?
Yeah, it's okay.
Then thank you very much for having me, giving me this opportunity to present what we are doing, and thank you very much for your flexibility with the order of the talks, with my confusion about the time zones. I'm very sorry about that. I also hope that you will have some understanding that my presentation will be slightly less scientific because of the confidential nature of our work, but I hope it will be anyway interesting to see what we are actually doing in the field of optics and then applying optics. Before diving into that, a couple of words about myself. Before I worked in an industry job, I was also studying. I did my PhD in physics at KIT in Karlsruhe, doing some superconducting quantum circuits and working on the properties of granulum aluminum nanowires. Actually being taught cryogenic physics by physicists from the Institute of Low Temperature Physics in Kharkiv, with some cooperations with them also. And since 2021, I work at Carl Zeiss SMT in Oberkochen in process development for high-NA EUV optics finishing. Since 2025, I'm a senior scientist with them. Yeah, I've added a picture of me fishing in Kupensk in 2020. So let's dive in. Zeiss. I have no intention and also not the time to give a company biography here, but I want to anyway point out two aspects which I find interesting. The first one is that Carl Zeiss, after founding the company in 1846 already, it's an old company. You might know the logo from maybe microscopes you've been working with, or prescription glasses, or camera lenses. But the company has a really wide field of work. And since the beginning, together with his partner Ernst Abbe, one of the biggest contributions of this company was to introduce a scientific approach to the development of optics. Prior to that, a lot of creation of optical instruments was based on trial and error, and they together first introduced a real scientific approach, for example, deriving the formula for optical resolution. The second aspect I want to point out is that since the very beginning, Zeiss understood themselves as providers and enablers of the work of others, be it in the field of medicine or science. And this philosophy basically holds on until today, with things that we are proud of even today, like eyes being treated with our technologies, or camera lenses that went to space. And especially I want to point out today this aspect in the top middle here, that nowadays about 80% of all microchips worldwide are actually made with Zeiss optics and ASML lithography systems. And in the high-end computing industry, I'd even say it goes close to 100% nowadays. That is only possible because we're a company heavily based on R&D. Last year, we invested around 1.5 billion euros into R&D, which corresponds to like 15% of our revenue. And this makes Zeiss SMT, like the semiconductor manufacturing branch, also in the top 10 of German companies when it comes to patent applications. As you already heard, we're quite a big company. We're visible to a lot of people in the consumer markets by prescription glasses, camera lenses, binoculars, and all these things, where also a lot of employees work. But I want to today focus on our part of the company, the semiconductor manufacturing technology company. We're also quite big in revenue, the biggest part of Zeiss nowadays, and we are operating from Oberkochen, a rather rural area in southern Germany, where we've been located and where also the Zeiss headquarters are located, basically since after the Second World War, when Zeiss physicists were moved from Eastern Germany under Soviet occupation to the Western German part, and where after German reunification, after Soviet Germany collapsed, the company was also reunited here. It's a big company, as you see. There's a lot of building ongoing. Here in the back are our manufacturing halls and where R&D is taking place. So what actually are we doing in our R&D, and what are we focusing our research on? That is basically pushing the limits of what is technologically possible with optics by continuously working on the forefront of lithography systems. On this plot, you see the resolution in nanometers of lithography systems over time. On the x-axis, it's an exponential, like a logarithmic scale. So it's getting exponentially smaller and smaller, all the structures. As you know, computers getting exponentially faster and faster. And this increase in computing speed is basically driven by our ability to exponentially increase the resolution of these systems for which we provide the optics. These bubbles in colors here are basically showing you different optical systems for lithography systems that work on different optical wavelengths. Each color corresponds one step in changing the optical wavelength. And inside of these bubbles, of course, also other things have been changed, like introducing immersion technologies in these optical, in these projection objects. Nowadays, like the current R&D is focusing, of course, on the EUV business. That was the latest jump to 13.5 nanometers, incredibly small wavelength, to achieve the even higher resolutions nowadays required. And this is still based on this formula, like derived in 1800s, where you can see if you want to decrease the distance between objects that you can resolve, you can either decrease the wavelength, which we've done by moving to EUV to 13.5 nanometers, or increasing the numerical aperture, which we've also done by moving to the high-NA projection optics. And these optics are in no way comparable to camera lenses or anything. They are huge, huge optical instruments with very many parts and yeah, really big. Of course, all of this in the end works only when it's implemented into a machine that works with it. These are the lithography scanners built by ASML in the Netherlands. And such a scanner is depicted here. And basically our optics are the part here with the light depicted in blue. And it's been said by, for example, a fellow at Intel that this machine is actually like one of, if not the most complicated machine that's ever been built. And the complication really comes in every part of this machine. I brought a small video by ASML actually that has a fly-through through this kind of a machine. We can have a quick look. I think it's interesting to see. Yeah, so that's basically how it looks, what the machines are doing. And the question would be, of course, what is so complicated in achieving all that? And as I said before, I think the honest answer would be really every part of this machine, be it the mechanics of the wafer and reticle stages that move with these incredible speeds, allowing 4 nanometer of overlay precision, be it the light source where this 13.5 nanometer EUV light is created, that is built by another German company, Trumpf. But of course, for me, coming from ZEISS, I must say that for me, the most fascinating part is the precision of the optics involved. When you go to 13.5 nanometers, it's a wavelength that's incredibly short and that is basically absorbed by everything. Like all the gases would absorb this wavelength, meaning that and glass also, we can't build lenses, transmissive lenses for this wavelength anymore, meaning that we have to create mirrors. So the optical lenses in our systems are actually mirrors, which can become quite big, as depicted on this picture here. And these mirrors then also have to operate in vacuum, for instance. So how do you make a mirror for EUV lithography? It's basically a Bragg mirror. Such a mirror consists of more than 100 extremely thin layers of silicon and molybdenum, which are alternatively applied to the glass substrate of these mirrors, and then in the end allow up to 30% reflection of EUV light, which is also a world record and is extremely difficult to accomplish with the precisions required. So there goes, of course, a lot of R&D and know-how, and there are a lot of problems that have been solved at our company in being able to fabricate these coatings. And I'm very sorry that I cannot go into more detail about that, since that's really strictly confidential. But one can sum up basically the challenge is to get the correct light to the correct spot reliably over many years. We don't have to do it in a lab once. It has to be done at the chip manufacturers many times over many years, without the systems breaking, and in many systems that we manufacture. For the mirrors themselves, that means that they have to be extremely precise. They are the most precise mirrors that have been ever built. To imagine it a bit better, there is this comparison. Like, let's just for a second assume we would have to build a mirror that is as big as all Germany. Like, the surface of the mirror should be as big as Germany. And then you can ask the question, how big is the largest deviation allowed to be? And the answer is, if the mirror was as big as Germany, the largest deviation from its nominal shape would be just 0.1 millimeters. That's how flat it is. It's as flat as Germany, as flat to 0.1 millimeters. Or to say it in different words, the mirror surface in our company is really actually measured in the subatomic level. And that's a challenge through the whole process chain, of course. Another comparison is that if you'd fire a laser beam at our mirrors and project it all the way to the moon, 390 kilometers away, the mirror surface would allow for a beam so precise that it would be no bigger than a golf ball when it hits the surface of the moon. And how we're doing that, that's of course been enabled by a very complex process chain through the whole of our company, which is designed from start to the finish, starting of course with the glass substrate, by the choice of what glass material we use, by grinding it into shape, by then polishing it, also of course computer controlled, fine figuring of the optical surface by ion beam figuring, and then coating the actual EUV coating on top of that. Where then we also have in this process chain a lot of things that we do not talk about, but even in these methods, which can be found in literature, which are known optical methods to fabricate optical lenses and mirrors, there are a lot of the parts of this process chain which has been developed and derived by ZEISS, be it in cooperation with industrial partners that then manufacture these machines, or being built by ourselves, like these heads of these polishing robots, for instance. For a physicist working in this field, it means that there are interesting questions arising along all the process chain. And in the end, of course, all this is only enabled by also being able to actually measure it. As I said, we have to measure at the subatomic level to be even able to tell the machines how to how to affect the mirror surface. And for this, we have built our own measurements tools, which has been one of the Zeiss specialties since the very beginning, from the start where Zeiss built microscopes to nowadays where they build these very huge machines that are able to measure these big mirrors on the subatomic level. For the work, it means that the whole company works as a very tightly knit machine, starting from the actual optical requirements in our design departments, deriving the design of the optical system, and then the requirements for the precision, for instance, and then being able to develop the processes that are able to manufacture these lenses in the required quality. As I already mentioned, not only once in a lab environment, but in an industrial scale. So there has to be a big step to be able to actually introduce this manufacturing step into the manufacturing shop floor, where it's been manned and done by specialized workers, but not by physicists and engineers all the time. And then, of course, there's always a continuous evaluation and improvement involved. And all of this has to be, of course, optimized also for cost. Like nobody has any benefit if we are able to do it once, but nobody is able to afford the machines we're actually building. Yes, and with that, I'm also at the end of my presentation. I'm open to questions.
Thank you. Any question, please? I have a small question. How do you measure your mirror at this subatomic level? What does it mean? So which physical methods do you use for such measurement?
Well, as sorry as I am, I'm really not allowed to go into much detail here. It's as well established in the optical field that there are some interferometric measurements involved, but how that works exactly, I'm very sorry, I'm not allowed to tell.
Okay. Are there any questions on the web? No? Okay, thank you, Yannick, for your difficult presentation. We are going to the next talk.
Thank you very much, and thanks for the opportunity to share it with you. Thank you.
Thank you. Denis Pugachev from the Institute for Single Crystals, DFT study of point defects in yttrium sesquioxide oxide doped with zirconium. Please upload 15 minutes.
So, good afternoon, ladies and gentlemen. My name is Denis Pugachev. I am a PhD student of Kharkiv Institute for Single Crystal. My scientific supervisor is Dmitry Efil, and I am honored to present you my topic, a DFT study of point defects in yttrium sesquioxide oxide doped with zirconium. So, various oxides are commonly used as sintering additives in the production of high-quality yttrium oxide ceramics, with zirconium oxide being among the most effective. During sintering, zirconium is incorporated into the yttrium oxide lattice, and the system remains single-phase, even at relatively high zirconia concentration, exceeding 20% of zirconia oxide in starting mixture. A characteristic feature of zirconium-doped yttrium oxide ceramics is that the lattice parameter is smaller than undoped yttrium oxide. It is generally assumed that zirconium ions are incorporated into the yttrium oxide crystals as substitutional defects on yttrium sides. In this case, zirconia ions are predominantly in the +4 valence states, replacing yttrium in +3 ions and creating positively charged point defects. Charge compensation occurs through the formation of additional negatively charged intrinsic defects. The main compensation mechanism can be expressed as these two formulas. You can see them, number 1, number 2. Yeah. The aim of this work is to investigate the energetics of the point defects in the zirconia doped yttrium oxide and their effect on the lattice parameter using DFT calculations. Our results indicate that zirconium primarily incorporates as zirconium +4 ions, although under certain conditions, a small fraction, nearly 1 or 2% of zirconium +3 ions also can be present. The dominant compensation mechanism is mechanism number 1, first formula on the previous slide, complemented by the formation of negatively charged substitutional zirconia and interstitial oxygen complexes. The calculated equilibrium concentrations of zirconia ions at sintering temperature of 1735 degrees Celsius correspond to 27% of zirconia oxide. Moreover, our results show that mechanism number 1 leads to decrease in the lattice parameter. The dependence of the lattice parameter on zirconia concentration obtained in our calculations is in good agreement with experimental observations. So our methods and calculation details. All calculations were performed using the strictly localized atom-centered basis set implemented in the open source Siesta code, which is based on density functional theory or DFT. In this work, as isolated defect is defined as a single substitutional ions, interstitial ion, or vacancy well separated from other defects, whereas a complex defect is defined as 2 or more closely spaced defects. All calculations were restricted to the 80 atomic cubic unit cell, where the distance between periodically repeated point defects equal to the lattice parameter. It's nearly 10 angstrom. The calculated energies of the neutral substitutional zirconia defect in 80 atom and in 40 atom cells differ only by 0.015 electron volts. Therefore, these defects in the present 80 atom cells can be reasonably treated as isolated from each other. Yeah. So in this work, we considered the following defects. Substitutional defects of zirconia in A and D Wyckoff position in the charge states of 0 + 1 in unit of electron charge. Also, we considered oxygen vacancies in charge state of 0 + 1 + 2. Yttrium vacancies also in A and D Wyckoff positions in charge state of -3, interstitial oxygen atoms at 16C Wyckoff positions in charge state of 0, -1, -2, and complex defect of 1 substitutional zirconia defect and 1 interstitial oxygen defect. Next complex is 2 substitutional zirconia defect and 1 interstitial oxygen defect. And third complex is consists of 3 substitutional zirconia defects and 1 yttrium vacancy. These complex defect configurations were considered by substituting zirconia atoms into the yttrium sites located nearest to the oxygen interstitials or to the yttrium vacancy. The most stable configurations, those with the highest binding energies, were considered in the analysis. So we are moving next to our calculation. First were defect formation energies and equilibrium concentrations. The formation energy of defect in charge state of Q was calculated using this formula. Using this formula, where E with index def and E with index perf are the total energies of defective and perfect unit cells, respectively. R with index X and A with index X is a number of atoms of different types. It could be yttrium or oxygen or zirconia removed or added to the unit cells from the defect. mu with index X is a chemical potential of species X. Mu E is electron chemical potential, and E with index C is a modeling correction accounting for the spurious electrostatic interactions due to periodic images of charge defects. The chemical potentials of the atom entering into equation 3 were determined using the calculation energies of the compounds in equilibrium in phase diagram of zirconia, yttrium, or zirconia, yttrium oxygen system. Figure 1 shows the calculated phase diagram for zirconia yttrium oxygen system. 6 equilibrium points are identified where yttrium oxide coexists with 2 other phases. These points are labeled as A, B, C, D, E, and F. The corresponding oxygen chemical potential mu with index O is also shown. The energy of O2 molecule per oxygen atom is used as a reference to mu O. Point from A to E correspond to reducing conditions, while point F represents the oxidizing conditions. Defect energetics at point E and F, where yttrium oxide is in equilibrium with zirconium oxide, are of our particular interest. So in figure 2, you can see defect formation energies at equilibrium points E and F, E on picture A, F on picture B. These energies of yttrium vacancy and substitution zirconia defects in 24B and 8A Wyckoff positions are shown as solid and dashed lines respectively. As seen in figure 2, positively charged zirconia substitutional defects are compensated primarily with negatively charged oxygen interstitials. Much higher formation energies of yttrium vacancies indicate that they play only minor role in charge compensation. As follows from the dependence in figure 2, negatively charged substitutional zirconia and interstitial oxygen complexes make an important contribution to the charge compensation of substitutional zirconia defects. Indeed, at the equilibrium Fermi level, shown as mu index E, determined by the charge neutrality conditions, energy of these complexes are lower than those of isolated interstitial oxygen defects. Those complex of substitutional zirconia and interstitial oxygen defects are predicted to play a key role in compensation in zirconia-doped yttrium oxide. The calculated formation energies of electrically neutral complexes of 2 substitutional zirconia and 1 interstitial oxygen oxide and complex of 3 substitutional zirconia and 1 yttrium vacancy are the same at equilibrium points E and F, with values of formation energy of 0.38 electron volts and 1.46 electron volts respectively. Figure 3 shows an equilibrium concentrations of charge, picture B, and neutral points, charge picture A, I'm sorry, and neutral points on picture B, defects at equilibrium points of on the zirconia yttrium oxygen phase diagram at temperature of 2008 kelvins. The concentration of ice defect species is given by this formula, where N is the number of available sites in the unit cell for ice defect species. Omega 0 is a unit cell volume, and T is a sintering temperature. As seen in figure 3, the equilibrium concentration of zirconia is very high at points E and F, reaching a concentration of 6 omega 0 minus 1, which correspond to 27% of zirconia oxide. This zirconia content is distributed almost equally between isolated substitutional zirconia defects and between complexes of 1 substitutional zirconia and interstitial oxygen defect, and complex of 2 substitutional zirconia defects and 1 interstitial oxygen defect. At point E, the concentration of ion of zirconia plus 3 reaches its maximum, about 2% of total zirconia content. Yttrium vacancies are mostly bound in the complexes with zirconia, but the contribution of such complexes is small, involving less than 1% of the total zirconia. At equilibrium points A and D, overall zirconia concentration decreases substantially. Next topic is impact of zirconia on the lattice parameter. The equilibrium concentration of zirconia at points E and F is higher than typical zirconia content in the raw mixtures used for sintering yttrium oxide ceramics. To account for this in calculations of the point defects concentration, we introduce this following condition. You can see this formula where the overall zirconia concentration is in the crystal is written in C with index zirconia total. The C is considered as external parameter. To estimate the dependence of the lattice parameter of total zirconium concentration, we sum the contribution of defects into the change of the unit cell volume. Our calculations reveal that only isolated interstitial ion defects increase the unit cell volume, while is isolated zirconia substitution and a pair of defects, substitutional zirconia and interstitial oxygen defects, and complex of two substitutional zirconia and one interstitial oxygen defect. So all these complexes lead to the volume reduction in the unit cell. In this picture, you can see calculated dependence of the lattice parameter for yttrium oxide doped with zirconia. It is shown with solid line compared to the experimental data from these scientific articles. They're given, they're written lower. So first data from first article is shown with diamonds, and data from second article is shown with squares. Index with index 0 is the lattice parameter for pure yttrium oxide. So one can see that although the model does not reproduce the non-monotonic behavior reported in article number 2, it provides quite good linear fit with experimental data. So to summarize all our data, our calculations of defect formation energies in situ for zirconium doped yttrium oxide leads to the following conclusions. The primary charge compensation mechanism for zirconia plus 4 ions involved zirconia substitutions and interstitial oxygen ions. Zirconium is distributed almost equally among the isolated substitutional zirconia defects and among the complex defects such as pair of zirconia substitutional and oxygen interstitial defect, and complex of two zirconia substitutional and one oxygen interstitial defect. All these defects reduce the lattice parameter of yttrium oxide. This model provides a satisfactory, nearly linear description of experimentally observed lattice parameter dependence on zirconia concentration. That's all. Thank you for your attention. You can ask your questions.
Thank you, Denis. We are open for discussion. Questions?
Yeah.
How did you choose positions for oxygen interstitials from oceans?
Thank you for this question. As I said, it was dedicated to specific like of position. Yeah. Near to atomic center, near to the defects, near to to yttrium vacancies, or something like this. So it was choose due to energetic properties. Yeah.
Any questions?
And I would have one, if I may.
Yeah, of course.
Thank you for the interesting presentation. Just to understand it better, so you did the calculations for the temperature of 1735 degrees centigrade, right?
Yeah.
And at that temperature, the result would be that you have actually the solubility of zirconia of 27 molar percent in yttria. I mean, is this one of the conclusions or not?
I'm sorry, could you repeat, please?
Okay. No, because you mentioned like you can go up to 27 molar percent of zirconium oxide. So does that mean that in principle it should be soluble up to this concentration in yttria at this temperature? That you would still have a solid solution with the 27 molar percent of zirconia.
Experimentally observed solubility of zirconia in yttria is of zirconium ions in yttria is about 21%. So that's the question. 27.
Yeah.
How we obtain?
So it was so this so our investigation were like theoretically to describe these methods. That is why we increase potential amount of zirconia oxide to recreate theoretically recreate these defects and to make them periodically and to give a theory to the practical to experimental data. So
okay, so it was the input, it was not the result, let's say.
Yeah.
Okay. It will be interesting how also that then corresponds to the room temperature situation. But I really, if you didn't publish it yet, then I'd be interested in reading the results at some point.
Okay.
Thank you.
I also have some small questions. Is it possible, for example, to calculate defects connected with fluorine substitution yttria, because we have such a report today?
Yeah, using the CS and DFT methods, we can choose. So there are big library of so the potentials of different atoms and so on. So if you need, you can choose them from open library, or data is checked through the experiments. It gives a very strict result. Yeah, so if you want, you can calculate for fluorine or other dopants, other dopes.
Okay, thank you. Are there any questions? No, thank you so much.
Thank you.
It's time to this next talk. I invite Konstantin Permas from Institute for Single Crystal to make native and carbon-related point defects in yttrium aluminum garnet, a first principles study.
How much time do I have? 15 minutes or 10?
15 minutes with questions.
With questions?
Yeah. If you need more time.
My topic is we study point defects in yttrium aluminum garnet doped with carbon. The formation energy of a defect can be found from equation 1. This energy depends on here E depth is and E perf is the total energies of defective and perfect unit cells. Numbers R and A is the number of atoms which are removed from the unit cell or added to the unit cell to form such a defect. Mu A is the chemical potential of atom of type A. where A stands for yttrium, aluminum, oxygen, and carbon. Mu E is the chemical potential of electrons. The chemical potential of electrons. Q is the charge of a defect, induced elementary charge. We consider two growth variants of YAG when it is growing in under the conditions with excess of aluminum oxide, and the second case, a second variant when YAG is growing under the conditions with excess of yttrium oxide. These conditions can be written in the form of such equations for chemical potentials. Equilibrium concentrations of defects of type E can be found from this equation. Here, Ne and I is the number of ways to put a defect of such kind into the unit cell, and V cell is the unit cell volume. This energy is the formation energy of such defects. The chemical potential of electrons is unknown quantity. It can be found from the charge neutrality equations. Equation 5. Here, Ce and Ch are the concentrations of electrons and holes. Energies, formation energies and the concentration depends on chemical potentials of atoms. Chemical potentials depends on we consider the case when a YAG is growing in the atmosphere of that contains gases of carbon oxide, carbon dioxide, and oxygen. For gases, we need to take into account the temperature and pressure dependence chemical potential. Chemical potential can be written as a zero part, which doesn't at zero temperature, and temperature and pressure correction. For gases, this correction term can be found from equation 7. Here, P is the partial pressure of such a species of oxygen or carbon monoxide or dioxide. P0 is the normal pressure, and some constants related to the molecules. For solids, we calculate this correction term using equation 8. Here, H is enthalpy and S is entropy. We use experimental data for H and S, and we neglect pressure dependence for solids, calculated in the normal pressure. For YAG melting temperature, we make calculations for YAG melting temperature. For YAG melting temperature, which is 2213 kelvins, and normal for such temperature and for normal pressure, we have such experimental data for this correction terms, which is written as equation 9. It's experimental data. When we, the first case, we consider the case when YAG is growing under the conditions with carbon oxide without graphite. Then we have such a reaction when CO reacts with oxygen and turns into carbon dioxide, which can be written as equation 10. If we substitute equation 6 and 7 in equation 10, we can find equilibrium condition for normalized partial pressures. This is equilibrium pressures. This is equation 11. K1 is a constant, which for melting temperature can be calculated as 5. the carbon chemical potential can be found from equation 12, which from the chemical potential of carbon oxide and chemical potential of oxygen. Okay? This chemical potential depends on equilibrium pressures. We take oxygen chemical potentials and total partial pressures, total pressures of carbon oxide and carbon dioxide as independent variables. And these quantities, these parameters, fully determine the chemical potential of carbon with equations, with this equilibrium equation. The results calculated concentrations, equilibrium concentration calculated for two cases, aluminum oxide rich and yttrium oxide rich conditions differ only slightly. So we present results only for aluminum oxide rich conditions. The minimal oxygen chemical potential in this environment can be found from equation 13. We take experimental data to calculate the minimal oxygen potential. Here are the results of our calculation for such case. We take the total pressure of carbon oxide and carbon dioxide as 0.1 and plot the formation energies as functions of chemical potential for electrons. Here, different slopes corresponds to different charge states. We consider three cases: strongly reducing conditions, moderately reducing conditions, and moderately oxidizing conditions. The chemical potential is written here for such cases. For the strongly reducing conditions where the chemical potential is minimal, the lower crossing points of positive energies of negatively and positively charged effects corresponds to defects of substitution of carbon for oxygen of CO minus and VO plus. And this is their energies are the lowest, so their concentrations are highest in such conditions, under such conditions. In the moderately reducing conditions, the charge neutrality is maintained mainly by oxygen vacancies plus with charge +1 and aluminum vacancies of charge -3 and interstitial oxygen with charge -2. Carbon-related defects are less favorable. In these conditions, their energies are higher. In moderately oxidizing conditions, the substitution of aluminum of carbon for aluminum, such C aluminum with +1, these defects dominate. These defects are preferentially located at tridal sites. The formation energies and at octahedral sites are higher. The charge compensation in this regime occurs via negatively charged vacancies of aluminum and yttrium with charges -3. Here are the results for complex defects calculated at the same for the same parameters as in the previous slide, at the same parameters. One can see that the energies of complex defects are higher than isolated defects under all conditions. The energies are higher. On this figure is presented the calculated equilibrium concentrations are presented for parameters for melting temperature of YAG and total pressure as 0.1 in the absence of graphite. We can see that under reducing conditions, the largest concentrations corresponds to defects of CO -1 and -2, and complex defects of CO- and oxygen vacancy uncharged, and CO2 minus oxygen energies or oxygen vacancies uncharged. The concentrations of complexes is in 2 orders smaller in value that concentration of isolated CO. In oxidizing conditions, carbon predominantly is incorporated as C aluminium +1, and the concentrations of complexes with cation vacancies constitutes 1% relatively to C aluminium +1. And at the moderately reducing conditions, the concentrations of all carbon defect species are low. Then comparing with oxidizing and reducing limit. Here, on these figures, we present the equilibrium concentration of oxygen and cation vacancies at the same parameters as previously. One can see that that carbon doping leads to significantly increase of charged oxygen vacancies concentrations, VO +1 and VO +2. In the oxidizing limit, the concentrations, carbon doping leads to slightly decrease of concentrations of oxygen vacancies and slightly increase of concentrations of aluminum and yttrium vacancies under oxidizing limit. Now we can see there's a case when we have graphite. We grow. We consider the case when yak is growing in the presence of graphite. In this case, we should take into account this reaction when carbon interacts with oxygen and turns into carbon oxide. This can be written as equation 14. This equilibrium equation must be considered with previous equilibrium condition of CO and CO2. From this equation, we can find equilibrium condition 15. K2 is a constant. It depends on temperature. For melting temperature, we obtain 16.3. To make in this case, a carbon chemical potential is fixed by the graphite, and it depends of mu. It is a constant calculated from graphite. We choose a parameter, oxygen chemical potential, as a parameter, and plot the equilibrium concentrations. Here on the left figure is concentrations where without graphite, and on the right figure concentrations when in the presence of graphite. We can see that in the presence of graphite under strongly reducing conditions, the defect concentrations are lower. Here, the total concentration of here's the total concentrations of carbon in CO containing atmosphere and in the presence of graphite. Blue, red, and green curves corresponds to 3 parameters: total pressure 10 power minus 1, 10 power to minus 3, 10 power to minus 5 in the presence of graphite, and black. And the black curve corresponds to the case when when yak is growing in the presence of graphite. We can see that all these curves have a minimum, the minimum under the moderate reducing conditions for all the cases. Thank you. My time is over. I don't think I should read the conclusions. My time is over.
Maybe main conclusions, 2 or 3 main conclusions.
2 or 3 main. DFT calculations combined with experimental thermochemical data allow us to predict the equilibrium concentrations of carbon-related and native defects in YAG growing in carbon oxide atmosphere. These equilibrium concentrations depend on the equilibrium partial pressures of carbon oxide and oxygen in the growth atmosphere. And these partial pressures can differ between two YAG growth variants without graphite and in the presence of graphite. Under reducing conditions, carbon preferentially forms substitutional of oxygen for carbon defects with charges +1 and +2. Under oxidizing conditions, substitutional defect of aluminium carbon for aluminium with +1 are the most favorable. Carbon doping significantly increases the concentrations of charged oxygen vacancies under reducing conditions, and the total concentrations demonstrates the minimum at the intermediate oxygen chemical potentials, and increases in strongly reducing and oxidizing atmospheres. Oh, thank you.
Thank you, Konstantin. Now we are open for discussion. The questions, please. Is there any questions? Oh, please speak louder. Thank you.
Question?
For neutron substitutions. Yes.
Can you speak louder?
So, have you performed calculations for carbon yttrium substitutions?
Carbon yttrium? No. Carbon yttrium.
As I understand, the ion reduced is quite different. So,
Carbon yttrium, no, we didn't make such calculations.
Okay, and maybe you can predict the concentration current to your latent for them.
We could, but we didn't calculate such defects. We calculate only C aluminium, C yttrium. We don't calculate such defects.
Any questions?
Yes, I have one maybe.
Yeah, of course.
So in YAG, usually we can see some gray or dark coloration under reducing atmosphere. And it's generally improved by silicium doping. Do you think that could be any interaction between silicon ion, carbon ion, oxygen vacancies to explain this coloration?
I don't understand your question. I'm sorry.
В монокристалах вітріалюмінієвого гранату зазвичай спостерігається забарвлення, пов'язане з карбоном. Чи спостерігали, тобто його можна позбутися шляхом добування іонами кремнію, чи спостерігали ви, що добування кремнія може знизити концентрацію іонів карбону або вакансії кисню в системі?
We don't consider the silicon at all. We don't consider such. We don't make such calculations. We don't take into account the silicon. We consider only carbon-related defects. So I can't answer your question because we don't consider the silicon defects.
Maybe next step of your calculations?
Oh, maybe.
Okay.
Okay, thank you.
Any other questions? Okay, let's start with our next talk before the lunch. Anton Zabucha, influence of optical and recombination losses on the performance of thin film solar cells based on complex heterojunctions. Sumy State University, Ukraine.
Okay, thank you. Good afternoon, everyone. I'm pleased to present to your attention a report on the topic influence of optical and recombination losses on performance thin film solar cells based on the tetrahydrate.
A bit louder, please.
Louder?
Oh, yeah,
Okay. First and second generation solar cells already show high efficiencies from 21 to 29%, approaching the Shockley quasar limit and highlighting their maturity. However, large-scale deployment of these materials is hindered by limited resources like cadmium and indium, and toxicity issues considering selenium and cadmium. Otherwise, castrate compounds offer an alternative, but their efficiency remains limited because of structural complexity and effect-related losses. The development of new, more efficient and structurally simpler materials for absorbing layers is still a key objective for next generation photovoltaics. So we are talking about tetrahydride, whose formula includes copper antimony sulfide, CAS, and it is a promising third generation photovoltaic absorber made of non-toxic and as abundant elements. It usually exists as a degenerate p-type semiconductor with a very high Hall concentration, and when doped with +2 oxidation state transition metals like zinc, nickel, or manganese, and selenium, it becomes non-degenerate and exhibits a very high absorption coefficient, up to 10 to 5 per centimeter, enabling the use of ultra thin and flexible and maybe transparent solar cells. So the problem is that practical thin films with this compound have efficiencies less than 1.5% due to energy loss mechanisms, and main loss channels include reflection of incident light from device surfaces and interfaces between layers, transmission of unabsorbed radiation, parasitic absorption, and recombination of generated pairs of electrons and holes at surfaces and within bulk region. So for improving the efficiency of these solar cells, it requires minimizing these losses via careful design and high quality layers. So our aim was, as I stated, for the first time to determine the impact of these losses on photovoltaic performance of solar cells based on tetrahydride. Employing an ITO front contacts, current collecting layers. We calculated the absorption capability, optical losses due reflection, and including absorption in auxiliary layers, recombination losses, including width of space charge region, internal and external quantum efficiencies, and of course, short circuit current density and device efficiency to determine the performance caused by losses. So to the methodology, the model employed analytical expressions based on continuity equation, incorporating factors that determine quantum efficiency, together with Sach noise Shockley theory for taking into account the recombination in space charge region. The absorbance of CAS is assessed using the Booker-Lambert Beer law, expression 1, and to find reflectance, we used Fresnel equations 2 and 3 with with it, we could determine the transition coefficients, expressions 4 and 5, also taking into account the absorption losses in the front and window layers. And so we considered the contact of two semiconductors forming a p-n junction, and that the contact interface rapid recombination of carriers occurs, leading to a formation of depletion region that extends into both N and P regions of heterojunction. The width of space charge region and window and absorbing layers in the window and absorbing layers was determined by expression 7, and it includes it is dependent on the height of the contact barrier, particularly, and to determine the height of the contact barrier, we had to construct energy band diagrams. So next we determine the internal quantum efficiency and external quantum efficiency. Internal quantum efficiency was determined as a sum of drift and diffusion contributions. And drift component accounts for carrier recombination at heter interface and within the SUR. And diffusion component accounts for recombination in the quasi-natural regions, aqueous and back surface. So, and as assumed, they whole internal quantum efficiency. The short circuit current density was determined with expression 12, and conversion efficiency with expression 13. When determining the short circuit current density, it is also we can use an equivalent circuit of ideal solar cell, which consists of parallel connection of current source and diode. And so next to the results. At the figure 8, you can see the absorptance of solar radiation, absorptance of photon flux, depending on the thickness of CAS absorber layer. Notably at thicknesses about 500 nanometers, its value is 80%, and at 2 micrometers it is up to 90%, and at figure 9 it is shown spectral dependencies of reflection coefficients at boundaries between conducting layers. We can say that these coefficients are not very are relatively low because of small difference between constants of materials used, optical constants. So next to transmittance, spectral transmission was determined with absorption and without absorption, and lowest optical losses was observed for zinc oxide and CAS heterojunction with values 93.3% and highest losses were observed for cadmium sulfide CAS heterojunction with the value 90.8. So the difference is quite small about surface area, and such small difference suggests that further optimization of solar cells should focus on recombination or quality of the layers. Table 2 presents the values of the offset of conduction band and valence band, and also all the values we needed to construct energy band diagrams. And you can see these diagrams on the right of the slide. And next to the internal quantum efficiency, it was found that lowering the accepted concentration in the absorbing layer leads to a decrease in quantum efficiency region less than 730 nanometers. That region corresponding to photosensitivity of absorber. And at the same time, when we increases the acceptor concentration, it results in decreased quantum efficiency, which is attributed to narrowing of space charge region. In turn, it increases the drift component of photocurrent and limits the performance boost. And about external quantum efficiency, it is also very important to take into account the transmission. And it shows that zinc magnesium oxide, obviously the window wire doped with magnesium shows highest values, especially at acceptor concentration 10 to 16 cubic centimeters, and donor concentration 10 to 17 per cubic centimeters. The thickness of absorber was considered 500 nanometers. And the next is the dependence of short circuit current density on the thickness of window wire. We also calculated it for different acceptor concentration, and notably optical and recombination losses cause a reduction in short circuit current density about 23 to 41%, depending on the acceptor concentration. And at this concentration 10 to 16 cubic centimeter, it exerts less impact on current density. Figure 15 at the right of the slide compares our simulated values with literature reported values for structures with similar compounds. And the next, table 3, presents calculated efficiency values at different acceptors concentrations. Notably, the most effective heterojunction was considered zinc magnesium oxide CAS. Window wire and current collecting wire thicknesses were 100 nanometer, and acceptor concentration 10 to 16 per cubic centimeter. Figure 16 demonstrates our simulated efficiency values and literature reported values for CIS solar cells. So to summarize, our simulations showed the optical and recombination losses have a strong impact on performance of tetrahedrite-based solar cells. We analyzed the absorptance of compound and found that wider bandgap windows not only enhance light transmission, but with magnesium oxide case, it has the best efficiency values. And it is obvious that doping zinc oxide with magnesium enhances the conduction band arrangement between window material and tetrahedrite, leading to increased open circuit voltage. That's the reason why overall solar cell efficiency is so high compared to the conventional cadmium sulfide or zinc oxide layers. Thank you for your attention.
Thank you, Optical. Please, we are open for discussion. Any questions?
I have one. So, by using your data, what can you do with your data? What devices maybe you could where can you improve with it, or where can you use it?
Thank you for your question. So basically, it's one step to the practical implementing tetrahedrite into effective solar cells, because before our work and before our theory and modeling, as I said, it had only less than 1.5% efficiencies, and we think that it is
related to the materials used in these works, like someone used undoped tetrahedrite, and it is crucial to dope it with zinc, as I said, for example, because simply it is what we want to do. We want to dope it with zinc and reduce its carrier concentration to use it in so absolute waves. Thank you. Thank you. Any other questions? Okay, well, let's thank Artem one more time. Now it is time for a lunch, and we will proceed with afternoon session at 2 p.m. Today. Okay, see you later.
Dear colleagues, it's time to start our afternoon session, and we will start with second keynote speech, which will be given by Sergei Nichankovsky, Institute for Single Crystals, Kharkiv. This topic of this report is growing of HighMatTech-2025 crystals with controlled doping distribution for powerful lasers. Please, for 40 minutes.
Thank you. Good afternoon, dear Roman and colleagues. Before I begin, I would like to thank the conference organizers for the opportunity to present my report, which is devoted to overview of recent global progress in the development of technologies for growing single crystals of refractory oxides for high-powered solid-state lasers, and to present the results obtained in Optical and Laser Crystals Department at the Institute for Single Crystals. From point of view of crystal physics, the high melting point is due to the high binding energy of its ions. This ensures the physico-chemical stability of refractory materials under various types of impacts and extreme operating conditions, particularly in high-power lasers with intense optical pumping. Oxide single crystals belong to such material. As well known, during the process of pumping and glazing, the crystal element heads up as a result of non-radiative transitions, Stokes shift, and various nonlinear effects. Due to the finite thermal conductivity of crystals, uneven temperature distribution occurs in them, leading to thermomechanical stresses and optical distortions, which limit the crystal's performance and at high pump energy densities. If an optical element is pumped with a certain energy density, the thermomechanical stresses in it can be estimated from the ratio, which will be determined by the so-called thermal stress resistance parameter, which depends on the mechanical characteristics and thermal conductivity of the crystal. The higher the volume of this parameter, the lower the negative thermomechanical effects and the higher the stability of the element. Thus, the thermal stress resistance parameter can serve as one of the main criteria for selecting crystal for use in high power lasers. Hundreds of laser crystals have been discovered and studied to date, but fewer than 2 dozen oxide compounds have found practical application. As the table shows, there are predominantly crystals with high melting points. Among them, titanium doped sapphire with its highest thermal stress resistance parameter. Yttrium aluminum garnet crystals doped with neodymium and ytterbium ions, which also possess a unique combination of thermomechanical and generation parameters necessary for use in high power lasers. As well known, dopant ions play a fundamental role in laser crystals. They absorb and convert pump energy into laser radiation. Therefore, controlled dopant distribution allows for the absorption of pump energy through the active element, thereby controlling the thermal field, which can significantly improve the operation and energy characteristic of lasers based on these elements. Depending on the crystal material, pump type, and element decision, an optimal dopant distribution is required. This distribution can be uniform, gradient, radial, or with a specific distribution function. Thereby, one of the current trends in the development of crystal technologies for high power laser crystal systems is the development of methods for growing crystals with controlled dopant distribution. This review will consist of two main sections, focusing on the most practically important titanium sapphire and yttrium aluminum garnet laser crystals. First, production and characterization of wide aperture titanium sapphire crystals for petawatt class lasers. Second, growth of gradient doped YAG crystal for high power diode pumped lasers. Titanium sapphire belongs to the class of vibronic crystals in crystals. In this lattice, the energy levels of the outer d electrons of titanium 3+ ions are greatly broadened due to electron-phonon interaction, resulting in broad absorption bands and record-breaking gain band of titanium sapphire from 660 nanometer to 1188 nanometer. This enables the generation of ultra-short pulses with duration of only a few femtoseconds. In turn, the short pulse duration and good thermomechanical properties of sapphire enable the generation of electromagnetic radiation of ultra-high intensity and power. The development of technology for growing high-quality T-sapphire crystals and the discovery of a new method for amplifying chirped pulses served as the basis for the development of ultra-high power petawatt plus femtosecond lasers. This discovery was awarded the Nobel Prize in Physics in 2019. Ultra-high power laser systems are promising for fundamental and applied research in the field of high energy physics, obtaining ultra-relativistic energies of photons and particles, as well as material science. To date, approximately 10 petawatt systems have been created and are under construction worldwide. Record pulse powers of 10 petawatt have been achieved. And new projects with 100, 200, and even 500 petawatt are planned. These crystals of the main of the main amplifier are subject to very stringent requirements for structural perfection and optical homogeneity. The output energy of a femtosecond pulse is proportional to the crystal area. So the crystal aperture increases with increasing of laser power. If obtaining a power of 1 petawatt requires crystals with diameter of approximately 80 to 100 millimeter. Achieving 10 petawatt required crystal with a diameter of 150 to 200 millimeters. One of the most important characteristics of the sapphire characterizing the level of optical losses is the form, figure of merit of crystals, which is defined as the ratio of the absorption coefficient for the absorption Y light to the absorption coefficient to the emission Y light. The larger the value of the form, the higher the optical gain of the crystal. Conventionally, for efficient generation, the form should be no worse than 100. Furthermore, the crystal volume must be characterized by high optical homogeneity with a wavefront distortion of no more than 1/4 lambda. Now we will consider the main methods and challenges of production wide aperture T-sapphire crystal for petawatt laser crystal lasers. Currently, there is a technology for production crystals with aperture up to 150 millimeter using the head exchange method, HEM. Experimental crystal samples with a record-breaking diameter of up to 240 millimeter have also been obtained. This method is a modification of the gradient phase method, where crystallization occurs by slowly increasing flow of helium gas, which removes head through the crystal seed. In this method, crystal growth occurs from the bottom up without direct observation of the seeding process and the phase interface, but only by monitoring the crucible surface temperature. This determines the technological challenges of this method, as it relates to finding and controlling optimal growth conditions. The main defects of such crystals are the formation of block structure due to unsuccessful setting of the formation of inclusion and dopant fractures at a suboptimal crystallization rate. For this reason, the entire process occurs at a slow rate. As can be seen in the photo, there is a noticeable radial uneven color distribution across the crystal diameter due to the distribution pattern of T3 plus ions. In cross section, the central region can differ by a factor of 2.5 in absorption for concentration titanium ions from the crystal periphery, with the lowest concentration is central. At the same time, relative uniform region with a diameter of up to 120 to 150 millimeter can form in the central region. This dopant distribution pattern is due to two main factors: the displacement of titanium ions with a segregation coefficient significantly less than unity, 0.60, and the curvature of the crystallization flow, which has the shape of expanding hemisphere. These factors result in the higher T ions concentration in the upper part of the crystal than in the lower part, and higher concentration in the edges than in the center. As I mentioned earlier, one of the key characteristics of titanium sapphire is the form. Crystal test shows a form value close to the minimum of 100. The problem is that in the emission region of titanium sapphire, about 800 nanometers, there is a broad parasitic absorption band caused by complexes based on titanium 3 plus and titanium 4 plus ions. It can be shown that the form is inversely proportional to the concentration of titanium 4 plus ions, whose charge is compensated by cation vacancies in the corundum lattice. Their concentration depended on the total titanium ion concentration and the partial oxygen pressure. Therefore, titanium sapphire is grown in the reducing carbon containing on hydrogen atmosphere. Clearly, the larger the crystal, the more difficult it is to achieve a high form value due to the presence of a large oxygen source in the bulk and the surface of the sapphire crystal and its melt. In the early 2010s, a French group began intensive research of titanium sapphire grown using the Chiropoulos method. Unlike him, in the Chiropoulos method, crystallization occurs from the top down onto a seed, and the growth process is controlled by reducing the heating power. The crystal does not contact the crucible, which allows for a low dislocation density. As a result of the experiments, titanium sapphire crystal with a diameter of 220 millimeter were obtained. It was found that the titanium distribution, similar to that in the hand, is axisymmetric and radial with a high concentration gradient from the center to the edges and the end of the crystal. A zone of relative uniform titanium distribution is absent within the crystal. This is due to the more complex shape of the crystallization form during growth using the Chiropoulos method. At the initial stage of growth, the front has the shape of a cone with a strong curvature in the apex, which first grows into the melt volume and then expand in the lower part of the chrysalis. When growing crystal using the Chiropoulos method, intensive convection of the hot melt occurs in the large chrysalis. The flows rise to the top and remelt the crystal, resulting in the formation of an elongated crystallization front, which serves as a concentric surface in the crystal, similar to three rings. Controlling the shape of the crystallization front is a very complex technological problem that requires a solution for the Chiropoulos method. Crystal form studies revealed a wide range of values, from 30 to approximately 160, depending on the point location. This was found to be due to the non-uniform distribution of titanium 4+ ions and the presence of scattering by submicron inclusion of a second phase. So, you can see, one of the main challenges in production wide aperture T sapphire elements for petawatt class lasers is the need to develop a technology for growing large size crystals that allows for efficient control of the distribution and charge state of titanium ions. Our department was the first which proposed a development alternative approach to solve these problems based on the horizontal directional crystallization method. This method is traditionally used for growing large single crystal plates and production optical windows from pure sapphire as well as doped crystals. The main advantages of this method are: first, low curvature and easy visual control of the crystallization form. Second, possibility of controlling the dopant distribution using bond melting. Third, the high ratio of the free surface area of the melt, so its volume is favorable for controlling the charge state of the dopant when interacting with the gas atmosphere. Fourth, The crystal has a dimension and shape similar to those of the final element. The curvature of the crystallization front in the crystal plane during the growth stage of the rectangular part does not exceed 0.1 and gradually decreases with increasing crystallization coordinate and crystal width, tending toward a virtually flat front. The front is slightly inclined relative to the perpendicular to the crystal plane. The shape of the front in longitudinal cross-section depends on the structure and intensity of convective flows in the melt and hair transfer through the crystal. A feature of titanium sapphire growth using the HDC method is the significant evaporation of titanium due to the large free surface area of the melt and consequently it depends on the distribution on the pressure and composition of growth atmosphere. The melt rapidly depletes when growth occurs in a vacuum and is observed distribution with decrease in titanium concentration along crystal, similar as in the case of the impurity with effective distribution coefficient greater than unity. We proposed using using zone melting with a gradient doping of the raw material load in the crucible to compensate for the non-uniformity of titanium distribution associated with evaporation, segregation, changes in the crystallization rate, and to control dopant distribution. In this case, the concentration of the dopant in the melt and accordingly in the crystal will change as the melt zone moves along the crucible. This method, in principle, allows obtain any specified distribution, including crystal with highly uniform dopant distribution. Phenomenological model of titanium mass transfer and distribution formation during growth by this method was developed to determine the required initial dopant distribution in the crucible for producing homogeneous titanium sapphire crystals. It was found that all other things belong equal. The initial longitudinal distribution of titanium in the load in the crucible is independent of the crystal width and directly proportional to the desired concentration and technological function. This function is multiparametric and depends on many physical and technology conditions and easier to determine experimentally. For this purpose, iterative method was developed that allows the technological function and initial distribution titanium to be determined with desired accuracy. As a result, using this method, we obtained crystal measuring 105 to 105 to 25 millimeter cubic, with a record high uniformity of titanium ion distribution of 0.001 weight%, which is difficult to achieve using other known growth methods. Furthermore, it was found the crystals are also characterized by a highly uniform distribution of various optical centers associated with titanium and vacancies. Consequently, the resulting crystals have a uniform form distribution at a level 120, 140. However, the question remains. It is possible to obtain large-size elements with even high form. The standard method of post-growth annealing is reducing atmosphere is limited by the diffusion of oxygen vacancies. We proposed using a preliminary carbothermic treatment of the raw material powders with the addition of carbon. Carbon serves to create oxygen deficiency and as bulk source of oxygen vacancies in sapphire, which lead to the reducing conversion of titanium 4+ to 3+ ions. As a result, we were able to reduce the titanium 4+ ion concentration was reduced by almost 4 times and increase the form of the large crystal up to 150, 200. Testing of titanium sapphire crystal growth using the HGC method demonstrated high optical and lasing characteristics comparable to the best world standards, as well as the possibility of their use in high power femtosecond systems. We now move on the second part of the report, dedicated to the technologies of growing yttrium aluminum garnet crystals with gradient doping. Diode pumped solid-state lasers have proven to be one of the most efficient methods for production of high power and high repetition rate generation. In the case of end pumping, traditional uniform dopant crystal will lead to the uneven distribution of pumping energy along the propagation direction due to the attenuation of pumping light by the absorption by dopant ions in the crystal rod. To solve this problem, elements with gradient distribution of the dopant along the propagation of the pump beam are used. In this case, temperature gradient and the optical lens effects are significantly reduced, which improves the beam quality and increases the generation efficiency. Gradient doped yttrium aluminum garnet laser crystal can be grown using the traditional Chakhrayskiy method and the segregation effect of the dopant with a low distribution coefficient, such as neodymium. However, for distribution coefficient close to unity, as with ytterbium doping, this is impossible. Our modified Chakhrayskiy method with double crucible or automatic dopant supply system is used to ensure the dopant enters the melt at a specified rate and its gradient distribution within the crystal. Disadvantages of this method, in addition to the relative complexity of dopant supply during the high temperature crystallization, is the high cost of the crystal production due to the use of very expensive iridium crucible and equipment. Simpler and less expensive solution to this problem may be provided by the previously used method of horizontal direction crystallization with gradient doping of the raw material. This method developed condition for growing garnet crystal in the vacuum or protective reducing atmosphere using thin-walled molybdenum crucible. It was shown that create a non-uniform step-shaped dopant loading allowed for a linear gradient distribution of ytterbium ions. The gradient magnitude is controlled by the phi of the concentration step. As a result, a large crystal up to 100 millimeter wide and with a gradient up to 3 atomic percent per centimeter of ytterbium will obtain. We have proposed another alternative method for growing gradient doped crystal using the HDC method. It involves using an additional crucible located within the main crucible and connecting by hole. This inner crucible serves as a source of dopant, which gradually enters the melt and crystal. The method has 5 independent parameters that allow flexible control of the distribution profile and concentration gradient. These parameters include the crucible dimension and their ratio, the dopant concentration, diameter of connecting hole, and the crystallization rate. If the crystal is pulled with a dopant fading and a non-stationary pulling rate over a certain distance to section 2 on this figure, this leads for the formation of concentration gradient in crystal. Then more slow down the growth rate, the more dopant accumulates in the melt and successively the concentration in the crystal increases. By growing with non-stationary pulling rate, it's possible to achieve high dopant concentration gradients over a narrow region of the crystal, which can be used to produce zinc terbium YAG gradient elements for high-power diode pumped disc lasers. In the limit case with growth stopping, a very sharp concentration step is formed in the crystal. In this case, the formation of stacking fault as a interface between crystal regions with different concentration was detected due to a significant change in the lattice parameters. Gradient doped neodymium YAG crystal were grown using the HDC method. A new type of neodymium YAG, the samarium YAG composite element with gradient doping of neodymium 3+ ions was created using these crystals. Diode pumping of such elements with total internal reflection demonstrated a more uniform distribution of absorbed energy and neodymium ion luminescence in gradient crystals. This made it possible to increase the efficiency of laser generation by 40% more than elements with uniform doped elements. Thus, today we have examined the main modern technology and challenges of growing refractory oxide crystals for high-power laser systems and demonstrated the wide possibility of the horizontal directional crystallization methods for controlling the distribution and charge state of dopant ions in laser crystal during a growth process. Thank you for your attention.
Thank you, Sergey. Now we are open for discussion. The questions, please.
Hello. Dr. Sergey, thank you very much for your very interesting and very nice report. I have one question. So how about the optic quality of such gradient doping ytterbium doped YAG single crystal compared with homogeneous ytterbium doped YAG single crystal?
Thank you for question. Gradient doped YAG crystals have optical quality comparable to uniform doping crystals YAG.
So what's the optical loss and what's the homogeneity?
Okay, loss about 0.001.
This is 0.001
Yes.
per centimeter.
Centimeter, yeah.
That means 0.1% per centimeter.
No, 0.001 centimeter.
I know, 0.1 percentage per centimeter.
Absorption on
this is absorption or
yes, coefficient absorption
or total optical loss.
Yeah. You understand me?
So what's the total optical loss of such gradient doping ytterbium doped YAG single crystal?
Absorption coefficient is about about 0.001 centimeter.
So this is only absorption. So how about scattering?
A little. Scattering, yes.
Yeah. How about the scattering?
Crystal maybe have some inclusions about micron size.
Macro size. I want to know the optical scattering loss and also optical absorption loss.
Оптичне розсіювання та втрати на оптичне розсіювання та втрати на оптичне поглинання.
We don't measure scattering losses. We measure only total loss.
Okay, so this is 0.1% per centimeter is the total optical loss.
Total optical loss on 1 micrometers wavelength is about 0.001 centimeter.
Okay, how about the optical homogeneity?
Optical homogeneity we research only for titanium sapphire.
Okay, not for such gradient doping single crystal.
Yes.
Okay, thank you.
Thank you.
Any other questions?
I would have one, if I may.
Yeah, please.
Thank you. It's been really interesting. I haven't seen some of those results before, so that was very nice. I was wondering if you could comment on the possibility, let's say, on the limits of the resolution of the gradient. I mean, like how, depending on the method, how sharp it can be, like, or how precise can the control can be moving from one composition to another. Like if you have the zone where you get from one composition to another, how thick that zone can be, or how it can be limited. For example, on the neodymium samarium example.
Yeah, I will translate.
Thank you.
Яке саме наскільки різкий там може бути перехід при градієнтному кристалі, наприклад, легована ітербіум, а як чітко ви можете підтримувати концентрацію в сегменті?
Okay, we can grow a crystal, ytterbium Yah crystal, with a stepwise distribution. But in this case, formation of stack and fault occurs at the interface with crystal region with different concentration. From this, this method allows to obtain crystals with different gradient up to maximum with obtaining a stepwise distribution. We have some experiment what shows that this method allows very good controlling concentration ytterbium in Yah crystal and gradient.
Okay, thank you. Yeah, and looking at here, I would say that you are, let's say, at least below one millimeter when moving from one to another, or is it really stepwise in the sense that at the micron level you have to really jump from one grain to another without a gradient, which seemed to be the case from the SEM?
Якщо зменшим шагом розглядати цей переходний шар, наскільки точно його можна власне плавно дотримуватись там діапазону констанції.
Sharp stepwise distribution we investigated by electron microscope probe method, and we show that distance where concentration is increasing is about less than 20 micrometers.
Oh, wow, that's impressive. Nice, thank you.
I have also small questions. Could you please show the first slide on gradient dot garnet crystals?
Second part.
Second part, yes.
Yeah, second. No, I
Second
mean,
part
I mean
presentation. Second.
the slide of the second part when you go to garnet composition. The first slide is garnet, not titanium. Yeah, previous. Yeah. Another one. Before. And yeah, before. And another. Oh, this one, yeah. I was wondering that the cost of gradient doped garnet is less than pure or homogeneous doped garnet. Is it true, or in general case, I think the gradient doped materials are a little bit higher in price, in my opinion.
Yes, gradient doped Yah cost is more than uniform Yah elements. Yes.
Okay. Are there any questions? If no, let's send to our speaker, and we are going to next invited speaker, which will be given by Alexandra Pina. I'm sorry if I pronounce wrong your family name.
It's okay, thank you.
Okay, the title of the speech is Growth and Optical Properties of alpha germanium dioxide single crystals. Now please share your screen.
Yeah, I will share it.
Yeah, and Alexandra is from University Grenoble Alpes from France.
Just one moment.
Yeah, awesome.
You don't see my presentation, isn't it?
Not yet.
Okay, and now it's okay?
Wait a minute. Oh, it's okay. Thank you.
Okay. Thank you. So thanks, I will thank the organization for letting me present my works about growth and optical properties of alpha GU2 single crystals. So this work has been done at Institut Nel in Grenoble in France, and you can see all the authors of this work here, and I thank them also for collaborating in this work. So I'm sorry. Yeah, it should be okay. Yeah, so this is the outline of my presentation. So I will give a brief state of the art of quartz crystals and GU2 crystals. In fact, GU2 crystals are of the same crystal family of quartz. So because of that, I will just explain a little bit the things that are the same in both of them and the things that are different. I will talk about the main properties of GU2 crystals known till date, that it's piezoelectricity at high temperature. Then I will just make a brief introduction of how this crystal has been grown. Then I will pass to the growth of these crystals in our group. So about the equipment, reproducibility of this growth process, the optimization of this growth process, about the morphology of the crystals that we obtain. And I will talk also a bit of the crystal of the quality of these crystals. And then I will finish with the optical characterization of these crystals, so nonlinear optical characterization and also the determination of the optical activity of these crystals. So what about the things that are the same between quartz crystals, so as SiU2 crystals and GU2 crystals? So they have the same space group, as you can see in the up part of the screen here. The growth method are different. In fact, for quartz crystals, the growth method is hydrothermal, and for GU2 crystals is hydrothermal. As you can see here, it has been done only once. So you can see here one quartz sheet, and then you have a heteropitaxial growth of germanium oxide. And I will discuss later why this is not working. And then we have the high temperature solution growth method. The crystals obtained, the first crystals obtained in our group, you can see it here in this picture. So quartz crystals, as you know, they are piezoelectric crystals until the phase transition, that is at around 500 degrees. And the birefringence C is quite low, as you can see here. And what about GU2? So GU2, it's a piezoelectric crystal until the melting temperature, until 1100 degrees, and has higher birefringence that it's good for nonlinear optical properties that you will see later on. So the problem by growing crystals of GU2 by hydrothermal growth is that we have a phase transition at around 200 degrees, and then another phase transition at 300 degrees. You can see here in the transparency window of GU2 that you have a band here coming from the hydroxyl group. And this is when the crystals are growing by the hydrothermal method. And this is why Go2 follows this phase changes. It's because of the crystals are full of hydroxyl groups. So when we grow the crystals by high temperature solution growth method, as you can see here, by X-ray diffraction, we follow the phase stability of the hexagonal phase, the trigonal phase. And as you can see here, until 1050 degrees, so just before the melting temperature of this crystal, the phase is the same, so there is no phase transition. So we can use these crystals, we can think that we can use this crystal for piezoelectric crystals at high temperature. And what about if we compare Go2 with other piezoelectric crystals? So you can see here a lot of crystals that has been used for piezoelectric crystals at high temperature. And we are in here, in this temperature. We want to use these crystals in this temperature range. And you can see here also that in this temperature range, you have GA PO4, that it's really interesting. And this is also a crystal that is of the family of quartz crystals that you can see in here also. And as you can see here, maybe Go2 is a bit better than phosphate of gallium. So because of that, we were interested in these crystals, and we try to grow big crystals of this of Go2. So what we know about the crystal growth process of these crystals? So we know that it has been tried to grow these crystals by high temperature solution growth method. The solvents that are used, you can see it here. So you can see here if they are grown by spontaneous nucleation or if they are grown by top-secret solution growth, the temperatures that they use to grow these crystals, and also the size of these crystals. So you can see here that the crystals were kind of small. So with a collaboration with a group in Montpellier in France also, they grow these crystals by spontaneous nucleation by using different solvents, as you can see here. So molybdate of rubidium molybdate of different stoichiometries, and also potassium molybdate. And here you can see what they obtain it. And as you can see here in the C1, they have quite bigger crystal and a bit more faceted ones. So then we try to grow with this flux Go2 crystals by the top-secret solution growth, and this is what we obtain. So it was possible to grow these crystals by top-secret solution growth. So what's next? Next was trying to grow these crystals in a bigger size. So we use a 3 zones furnace, as you can see here, 3 heating zones furnace. Here you can see the schema. You can see the solution in the crucible, platinum crucible, and here you can see the oriented seat. And we follow the growth process by a balance that you can see here. And the movement of the seat, it's done by this motor that you can see here. Everything that you can see in this schema, you can see it also in the pictures, that you can see the real furnace that we use, also the motor you can see here, and the balance that is just behind. This is one of the oriented seats that we use. We need to have an axial gradient that it's really, really close to 0 to have good quality crystals. This is one of the ones that we use. We also follow the growth during all the growth process, because we need to change the temperature during the growth process, and the rate that we change the temperature should be the good one to have the crystals that are good quality, and that we have a crystal growth rate that it's the good one. So here you can see at the beginning, we make also always a bit of dissolution of the seed, and then the growth begin. Here you can see the weight curve of during all the growth process. The growth process is in solution, so it's quite slow. So to grow one Go2 crystals, we need at least 1 month of growth. So here you can see at the beginning is this zone here, and then it grows till the end of the growth. That here in this case was 24 days. So what was the problem with this solvent that we use? So this is the one that told you that in Montpellier they make some spontaneous nucleation, and then we try to make some crystals in here. So the problem, as you can see here, this is 1 point, this is one temperature of one of the trials that we made, and these are other 2 temperatures of the trial. So this equilibrium temperature, so when the crystal begins to grow, changes a lot, in fact. And we didn't understand why, but then we just removed the solution when the solution was hot, and we see that at the down part of the crucible, it was always GO2 that it was not dissolved. So we changed the method to try to dissolve this GO2 that was not dissolving in our solution. So we tried to use glassy GO2 and not commercial hexagonal GO2 powder. And you can see here the molar compositions. And as you can see here, this is green points here. This is really reproducible if we use the glassy GO2 crystals. So this is what the good news. The problem was that we need to transform commercial GO2 powder into glassy GO2 powder. So, sorry. So as you can see here, this is the table. And we try different way of dissolving the GO2. So with the molybdate one, the solvent that I just told you, so this is what it was working. Sorry, the commercial one was not working. The solute dissolution was partial. With the glassy one, the complete dissolution was perfect. So the growth, it was really reproducible. And then we try also a mix of molybdate and phosphate flux with the commercial powder, not to have a glassy powder, so we can directly make the solutions with the commercial one. And here you have what happens. In fact, the solvent evaporation is really high or quite high when we're using molybdate, but it's not high when using the mixed solution that is molybdate phosphate. And even though it's not really high, the solvent evaporation, but the problem is like when finish the growth, we have to clean the crucible. And it was really hard to clean the crucible only using molybdate flux. And it was really easy to clean it only with hot water when we use the mixed flux that you can see here. So all the speriums that I will show you in this table comes from this system here, almost all of them. Only one, it's the first one here, it comes from the molybdate. But the other ones are always with the kind of mixed flux. So here you can see the orientation of the seed that you use, the rotation of the crystals, some of the growth parameters that we use. And here you can see the pictures of some of the crystals that we have obtained. So what about the morphology of these crystals? They always show almost the same faces, only sometimes they show these small faces when we are working only with molybdate flux. And what we are interested, in fact, is that these faces here that you can see here are the biggest as we can. So now we are working to do that, and we're trying to dope our solution with a bit of silicium dioxide. As you can see here, it changes a bit the morphology, and these faces that we want for some characterizations are bigger. So what about the crystals quality? So here you can have the rocking curve of an oriented 110 slab. So it's really nice quality. And here you can see one of the slabs that we just cut to make some characterizations, a big slab that it's really nice. And you can now see here a bit of the problem that we are trying to solve is that we have optical twins in these crystals, but I won't talk about this today. So we passed to the optical characterization. So as we have really nice crystals that with a good quality, we prepare a cylinder of these crystals, as you can see in here in this picture, and we make some nonlinear optical characterizations. Here you can see the phase matching curves of second harmonic generation, and here the ones some frequency generation and different frequency generation. So by these values that we have here and by the phase matching angles, we determine the refractive index of this crystal. So it's a positive uniaxial optical crystal. This has been confirmed. It was an old paper that says that, but it was kind of the refractive index were not really accurate. And here we determine the crystals with a good accuracy, and we also determine the nonlinear coefficient of these crystals. And we also make some calculations to see if we can generate a supercontinuum. And this is what we obtain. So we can generate a supercontinuum between 1.2 microns to 3 microns if we pump the crystal with a titanium sapphire laser at 0.86 microns. So then we have good refractive index, so we can guess that we can make some other optical determinations and use this non-refractive index. So here is the optical, the experimental setup that we use to determine the optical activity of these crystals. So we know that the optical activity of quartz is quite high, and we wanted to know also if the GU2 one was high also. So GU2 as quartz is a chiral crystal, and here you can see the shimmer of the light going through the crystal. And here you can see some of the graphs where we determine the rotatory power of this crystal, how we determine it. Here you can see the results. So we use our setup to try to make rotatory power also of quartz crystals to see if it fits well with the bibliographic data that we have. And we determine also for GU2 in the same wavelength range. So as we have a good refractive index determination, we can also determine the Giratian coefficient, G33, and we also did that with the optical activity and with the refractive index. And with this data, we determine an empirical microscopy model that it's based on a simple geometric approach that you can see in here, in fact, and that describes very well all the data that we obtain here, in fact. So now we are working on knowing which is the physical explanation of this value that we have here, and we will do it with by determining also the Giratian coefficient and also the rotatory power, so the optical activity of other materials that are of the family of quartz, that it's gallium phosphate and aluminium phosphate. So I will finish my talk. So I show you that we found the conditions to grow alpha GU2 crystals by top-C dissolution growth. Now we are trying to change a bit the morphology of these crystals by introducing some silicium dioxide in the solution. The size and the quality of the crystals allows to perform nonlinear optical characterizations and also optical characterizations, so determine the optical activity and the Giratian coefficient. But we have still a problem that I show you in the slab picture. We have still twins, so we are working to try to remove them. So thanks to all of you, and this is a project that has been done in two NR projects, that it's research projects, French research projects. Thank you.
Thank you very much for your nice talk. The questions, please. Can the methods you use to grow single crystals, can you control the size of the samples grown?
Yes. In fact, as we follow the weight of the crystals, and we know the superficial tension of this system, we can stop. If we want to stop before, we can stop. And the biggest one that we obtained till now, it's kind of 3 centimeters by 3 centimeters. It's not bigger than that.
Yeah.
And then, we can grow smaller, but bigger. With all the trials that we have been done, it's only 3 centimeters, sorry. Like the ones we can see up. swell. Like the ones here, it's 2 centimeters 5.
Okay. What is idea of doping by silicium dioxide?
It's because
it's to overcome problems during crystal growth?
No, the twins are still there. We have take a look to that. But in fact, we need some wire slabs to some characterizations that I didn't present, to surface acoustic wave characterizations and surface acoustic wave some kind of experiments. So this is why we are trying to change the morphology, to have Y slabs that are really bigger than the ones that we have till now.
Okay. Any questions? No. Okay, no questions. Thank you so much for your nice talk.
Thank you.
We are going to next speaker, Alexey Poloboyarov from National Aerospace University, Kharkiv Aviation Institute, Ukraine, who will present the talk, Subsurface electrostatic potential of submit zinc telluride crystals with different polarizability. Alexey, are you hear us?
Yes, I hear you. And do you hear me?
Yeah, it's okay. Please share the screen.
Great. Now I will share my presentation. So, can you see it?
Not full screen.
Maybe wrong window. One moment. So I think that's it, yes?
It's okay, yeah.
Yes, that's great. So good afternoon again. My name is Alexey Poloboyarov, and I am presenting from behalf of my colleagues from National Aerospace University, Kharkiv Aviation Institute, from Faculty of Radio Electronics and Computer System. And topic of my report is subsurface electrostatic potential of cadmium zinc telluride crystals with different polarizability. It's widely known that subsurface electrostatic potential is an important characteristic of crystals, semiconductors, that is determined not only by its structure and composition, but also by external influences. And moreover, doping impurities and intrinsic structural defects also affect the potential. Since the distribution of electric potential near the crystal surface plays a primary role in electronic processes, the study of this value is of significant importance in the development of a wide range of electronic devices, such as field transistors, solar elements, and so on. But I will speak specifically about one compound, cadmium zinc telluride, that is received by our colleagues in Institute for Single Crystals. It's ternary semiconductor solid solution, and it's, as usual, used in ionizing radiation detectors. And characteristic feature of all semiconductor solid solution and also of cadmium zinc telluride, and that they have different types of intrinsic structural defects and compositional inhomogeneities. And the study of these features obviously influence the subsurface electrostatic potential. So, to study this influence was the purpose of current work. We studied cadmium zinc telluride crystals with zinc content in range from 0.12 to 0.16, grown from melt by vertical Bridgman technique. Then we make rectangular specimens. Their surfaces have been processed to grinding, polishing, and etching to ensure removing damaged near surface layer. It's obvious because we are going to study subsurface electrostatic potential, so we needed clean surfaces. And then the conducting lacquer for studies was applied on them. We measured the resistivity and we measured complex dielectric permittivity of these specimens and chose the ones with real part of complex dielectric permittivity in range from 11.5 to 15.5 and the imaginary part from 0.5 to 33 respectively. That measurements were conducted at frequency of 1 kHz. And then we used our original scanning photodielectric spectroscopy method to measure subsurface electrostatic potential as well as the energy spectra of charge carriers localized state in those crystal specimens. I need to say that this method is based on measuring small increments of real and imaginary parts of complex dielectric permittivity of crystals, while we smoothly variate the wavelengths of incident monochromatic light. And the spectral dependencies allow us to acquire an energy spectrum of localized states of charge carriers and measure the surface electrostatic potential of crystals. Here on this chart, we see the dependence of subsurface electrostatic potential phi from real part of complex dielectric permittivity epsilon dash for studied crystal that we also measured at a frequency of 1 kHz. And it can be seen that it changes non-monotonically when we are moving to the specimens with the larger epsilon dash value. Here I should note that value for real part of complex dielectric permittivity 11.5 is usually stated in many literature sources as constant for this material. But in that frequency, we observed that specimens with the largest epsilon dash have a strong dispersion of this and both imaginary part of complex dielectric permittivity. And also analyzing spectra of localized states, we discovered that they are also characterized by an increased amount of localized state carriers that are detected by our method. We summarized this data in the table. It shows the energy spectrum of carriers of localized states that are measured in specimen with the smallest subsurface electric potential and the largest subsurface potential. And at the same time, the latter has the smallest value of real part of complex dielectric permittivity. Also, here are given information of energy levels of localized states in cadmium zinc telluride crystals known from literature, and the nature of these levels according to previous studies. It can be seen from this table that a significant part of localized states are observed on one specimen and is not observed for another. At the same time, they, as a rule, correspond to energy intervals for defects of certain time that were already known. So, how can we deal with it? In our opinion, as usual, we should take into account that for these ternary compounds are characteristic intrinsic structural defects that emerge during growth from melt, and they form the electrical properties of compound in general and for every single specimen individual. So, as a feature of solid solution is the presence of composition and homogeneity, which determine the individual peculiarity of the composition of such intrinsic defects in each studied crystal specimen. And at the same time, they differ one from the other in the set of localized state which came from our analysis. And in individual specimens, due to high concentration of defects of a certain time, electrons jump between adjacent defects under the influence of a measuring electric field, and in this case, the defects manifest themselves as electric dipoles. This is well accords to the model proposed for such ternary compounds by Zhukovsky, Rodzik, and Shostak, and it takes into account peculiarities of energy bands in such A2B6 compounds. So such jumps of carriers cause increased magnitudes of both components of complex dielectric permittivity, especially area 1, as was stated in that model, and we see it in our study. So it can be assumed that with an increase in concentration of intrinsic defects, the character of their influence on the subsurface electrostatic potential changes. So, conclusion from our study is that for the first time we observed a connection between the subsurface electrostatic potential and the real part of the complex dielectric permittivity in cadmium zinc telluride crystals in the low frequency region. And we assumed that this feature of the electrical properties is caused by intrinsic structure defects of the growth nature, which determine the energy spectrum of charge carriers, localized states, as well as the subsurface electrostatic potential of the crystals. But also we should state that establishing the exact mechanism of this influence of specified defects of on the subsurface electrostatic potential, as well as study this for other frequencies, require additional research. Thank you for the attention.
Thank you so much. The question, please. Yes. Есть ли зависимость сложности? То есть он писал, the properties of a solid solution will depend on the concentration of main components. Do you have you measured differences? Have you observed differences in potential you determine with concentration of main components?
No, we have not observed this because according to our previous studies and preparational, we, as I said, measured resistivity, we measured dielectric permittivity, and chose specimens according to this. So we didn't take, as I heard, another zinc concentrations.
По составу, то есть без данных по составу, so have you prepared the samples before the measurements? Have you polished or annealed or removed that layer?
Yes, as I said, it was mechanical grinding, polishing, chemical etching. All that was done also in Institute for Single Crystals. We only had these specimens and measured, as I said, subsurface electrostatic potential and acquired our spectrums.
Am I understand that you cut the slab into pieces, then prepared for measurements, and every part of the crystal has a different number of intrinsic or other defects. Am I right? Because when you look at the table, you ascribe different crystals have different defects. On the page, on the slide 5, you have table.
Yes.
Yeah, and supposed centers. So you have different number of defects, complex structural defects, zinc atoms, and so on. So it is from different part of the crystal, or it is just different position of energetical level of these defects?
Specimens was from different parts of several crystals. About that column, that is literature sources. So we compare energy levels that we discovered in our study for, as example, specimens with smallest value of subsurface electrostatic potential and the highest one with known earlier.
Understood. Any other questions? Okay, thank you very much for your report. And
Thank you.
We are going to next one. Arseniy Timoshenko from Institute for Single Crystals, Kharkiv, will have a report effect of grain size distribution on solid-state single crystal growth, Samarium gold gap.
Okay, hello, Alex, and as lithium aluminum garnet is one of the most important materials in quantum electronics, laser technology, and photonics due to its unique combination of optical, thermal, and mechanical properties. Samarium crystals, due to its optical properties, is considered the best candidates for suppressing parasitic oscillation in high-power neodymium-based lasers. The use of samarium ensure absorption, transfer mode, and spontaneous emission. Additionally, such suppressors contributed to more efficient heat dissipation. This allowed to simplify and minimization the lasers design without compromises in efficiency. Solid-state single crystal grow has been shown to be a promising technique for the growth of single crystal material. In most cases, the solid-state single crystal grow method uses a single crystal seed. The seed is bonded to ceramic by diffusion bonding or embedded during the compactation stage. Then conditions for abnormal grain growth are created by increasing the sintering temperature or adding sintering additives. The SSCG method offers many advantages over conventional single crystal grow technique. However, there are still many issues related to this technique which are not yet well understood. In particular, commercial production by this method is available only for barium titanate-based materials and lead-based piezoelectric materials. The main reason why this technique has been successful for only some limited system is the difficulty of achieving control over the microstructure of the initial polycrystal. The solid-state single crystal grow method utilizes the phenomenon of abnormal grain growth in polycrystal. Theoretically, one big grain or seed crystal scavenges all other grains in polycrystal, and the polycrystalline become a single crystal. But heated temperature, sintering additives, crystallographic orientation, average grain size, and grain size distribution have a significant impact on the single crystal growth process. For effectively single crystal grow by SSCG method, it's necessary to ensure high quality of contact between ceramic and seed crystal, and to maintain the conditions that driving force for the growth of seed crystal must be larger than critical driving force in ceramic. The critical driving force varies with temperature and doping. The maximum driving force is governed by the average grain size and grain size distribution. Therefore, the microstructure of the initial ceramics determines the driving force at the beginning of growth. One of the ways to control the microstructure of ceramic is to use sintering additives. The use of functional additives allow to selectively intensity diffusion process during sintering and to control the type distribution and grain size of ceramic. The most commonly used sintering additives for yacht ceramic are silicon oxide and magnesium oxide. The separated effect of silicon and magnesium ions on the microstructure of yacht ceramic is well known from the literature. But a more effective option is to use a combination of these additives. Changing the concentration ratio of the additives allow to control the microstructure in fairly wide range. To study the effect of grain size distribution on the solid state growth, ceramic sample with different microstructure were fabricated. Ceramic with a wide unimodal grain distribution and average grain size of about 12 micrometers. Ceramic with narrow unimodal grain distribution and average grain size of 3 micrometers, and ceramic with bimodal microstructure and average grain size of 2.4 micrometers were fabricated. After mechanical polishing, the obtained ceramic were diffusion bonded with an endowed single crystal yak seed. After diffusion bonding, the sample were heat treated at a temperature of 1775 degrees for 10 hours. It was shown that ceramic with wide unimodal grain distribution do not provide the condition necessary for single crystal growth by the solid state convention method conversion. The growth rate of a single crystal layer for sample with a wide grain size distribution is estimated at about 1 micrometer per hour. Much better results are observed in simple with fine grain. The growth rate for a single crystal reaches 6 micrometers per hour. However, for effective production of single crystal using solid state conversion, the growth rate must be much higher. Ceramic with bimodal grain distribution demonstrated high growth rates. No grain boundary is observed in optical microscope. This may indicate complete absorption of matrix grain by seed crystal. However, the XFD results show that is obtained simple with bimodal grain distribution in additional of the diffraction peak corresponding to the seed crystal, several peaks corresponding to YAG crystalline with different orientation observed. This can be explained by the formation of additional growth source during thermal treatment due to the high crystallization rate. During future growth, anomalous grain of matrix collide with the crystallization from seed, which lead to the emergence of several crystalline with different crystallographic orientation on the surface. Therefore, the obtained ceramic with bimodal grain distribution is unusable for transformation into a single crystal under this growth condition. And conclusion. It has been shown that the microstructure of ceramic has significant impact on solid-state convention process. Ceramic with dense homogeneous microstructure do not provide the conditions necessary for effective single crystal growth by the SSCG method. The growth rate is estimated to be about 1 micrometer per hour. In ceramic with narrow middle grain distribution demonstrate a low crystallization rate. The single crystal growth rate is about 6 millimeter per hour. The bimodal distribution of ceramic leads to formation of additional growth source, resulting in competent growth of single crystal in matrix. Also, the higher crystallization rate leads to interrupt of pores in the single crystal volume. Ceramic with bimodal grain distribution are unsuitable of conversion into single crystal under this growth condition. In future, more detailed study of conditions of obtaining single crystal by SSCG methods and optimization of impurity composition and heat and temperature obtained. Thank you for attention.
Thank you, Arseny. It's time for discussion.
Sandy, thank you very much for your very interesting report. I have one question. What are the advantages of semi-doped YAG single crystal prepared by the solid-state crystal glow method compared with the single crystal prepared by the conventional single crystal method?
Які переваги монокристал вирощеного методом реакції в твердій фазі в порівнянні з традиційними методами вирощування цих кристалів?
Okay, understand. By solid-state crystal grow methods, we can fabricate complex sharp products and more higher concentration of functional dopants as samarium or neodymium.
So, how about the chemical and optical homogeneity of the semi-doped YAG single crystal produced by the SSCG method?
Хімічна та оптична однорідність кристалів, які ви отримали, яка вона?
Unfortunately, that's simple what we prepared too small to measure chemical homogeneity.
How about the optical quality? Mainly, what's the optical loss of this sphenic single crystal by SSGCG method?
Can't measure optical losses at 60 micrometers and ceramic with bimodal grain growth not transparent.
So, did you measure the inline transmittance of such single crystal?
Линейное оптичное пропускание.
No.
In progress. Maybe it's in progress.
It will be.
It will be. So, you told us some advantages, but you can't give us the evidence.
Yeah, maybe yes.
Maybe.
Yeah, thanks for your report.
Thank you.
Any other questions, please? No? Okay, thank you very much, Arseny, for your report. And we are going to last oral report in this session. Igor Borona from Institute for Single Crystals will present his report advancing in laser ceramics for fabrication of composite active media, yak neodymium, yak samarium.
Greetings, dear colleagues. I want to present you report about some advances in laser ceramics in purpose to fabricate composite active mediums. Not working. Slide. Okay. Composite active laser mediums currently in high demand for different applications. There are plenty of configuration proposed to improve heat management, operation temperature range, optimize pumping, and increase power and efficiency of contemporary lasers. In particular, inter-aluminum garnet is a very promising material for such applications because of high range or wide range of available compounds with different activators used in for laser generation and supplement functions as parasitic oscillation suppression, Q-switch, and so on. But there are some challenges in this direction. Firstly, in many of in-demand configurations, some segments of composites require high concentration of activator, which is not not always widely available. And secondly, obtaining required complex shapes and jointing segments of composites, particularly in case of using aluminum garnet, is a challenging task because it's a hard and fragile material. In its turn, existing technology of yak ceramics based on solid-state sintering can be a very promising answer to these challenges. In a nutshell, ceramic technology, solid-state sintering ceramic technology can be described in three crucial steps. First is preparing initial components for future ceramics in a form of fine powder mixture. then forming the green bodies of desired shapes by dry pressing, cold-static pressing, or similar methods. And finally, annealing at high temperature in solid phase to achieve transparent state of ceramics. What important in our context of composite materials is that due to all process conducted in solid state, the resulted product is mostly resembles the shape of previously prepared green body. And method of green bodies obtained by forming the nanopowders is pretty convenient and allow us to make complex shapes with relative use. As example, how we can make a cladding structure by two-step pressing of nanopowders. But there are some problems. To make such composites in single stage or in single sintering, which is very efficient, we need to choose conditions of sintering. And as we can see in the table, the temperature of sintering for ceramics doped with different activators, with different dopants, differs. This results, in fact, from our works, and it's very comparable because all these materials obtained at the same equipment within the same base technology. So it's a real difference, and in result, if we want to prepare composite, we need to make some compromises in quality of part of segments. But if we can extend the consolidation range to at least 25 degrees Celsius, we can overcome this problem and to make better composites. So what we're talking about here? Here, as example, you can see ceramics doped with 1% of neodymium obtained with different temperatures using traditional additive based on ions of silicon. With increase in temperature, we can see a significant increase in grain sizes, and more crucially, changing the homogeneity of microstructure. At low temperature, we have small size. Sorry. How to use this red dot? So with increase in temperature, we can see that a bimodal distribution in grain sizes appear. That testifies of grain boundary phase transition, which leads to intense recrystallization, which escalates with bigger temperature. And finally, at some temperature, which in fact optimal for this compound, we finally have again homogeneous microstructure, but with much larger grains. What's happening here by this is problem? This is problem because as we can see, these changes in microstructure corresponds to significant differences in optical quality of ceramics. So we have a very high sensitivity to sintering conditions. What's happening? In a simple way, the process of sintering consolidation of ceramics with free sintering without pressure can be described as spending of free surface energy that existing is in initial powder mixture in two main sources. It's gray-grown, which decrease overall surface area and thus energy. And second, densification, which replaced free surface with less energetic interface between grains boundaries. The problem is when we have such processes of intensive crystallization associated with grain boundary transition and high mobility grains which grow fast. This process takes a significant amount of free surface energy from the densifications. As a result, we have suboptimal sintering trajectory and ceramic with less optical quality than desired. The idea in this work was to use a complex sintering aid which involves ions of silica and ions of magnesium to suppress grain boundary phase transition. Magnesium ions, unlike silica, when introduced into ethylaluminum garnet lattice, create anionic vacancies to compensate its bivalent charge. When silica creates cationic vacancies. Because of this, magni is more efficient like grain growth inhibitor, but not very efficient as sintering aid itself. Combining these two give us an optimal result if we can balance the concentration of cationic and anionic vacancies in ceramics. And by tailoring this silica to magni ratio, we achieved a following result for the also ceramics doped with neodymium, but with complex aid. We have a much more homogeneous microstructure through a wide range of temperatures, which we don't see any signs of grain boundary transition. And as a result, we have much less dependency of optical properties from temperature of sintering. We can obtain virtually the same ceramics in the range of 25-30 degrees of Celsius. Sorry. As a result, we see that using a complex sintering additive can give us a better optical quality overall, especially in short wavelengths, allow us to use lower sample temperature of sintering if needed, which can be very beneficial in technological and economic terms sometimes. And crucially for obtaining composites, we can avoid compromises when choosing sintering conditions for composite materials, consisting of YAG doped with different activators. And here can demonstrate that the similar approach was applied to ceramic doped with 3 atomic % of samarium. And here we can see that results have been this approach appear even more efficient with virtually identical transmittance and similar microstructure of ceramic within the temperature range of obtaining 50 degrees. Using this approach, we start to obtaining some composite, configuration of composite ceramics which in demand. Here in the left you can see, for example, layered ceramics doped with neodymium and samarium, and at the right is coaxial ceramics doped with terbium with undoped yak cladding. Here is ceramic as sintered in vacuum. It's we can see the central layer of terbi thanks to bivalent ions in it, and after annealing in retire conditions, we see that polarizing disappear, and with it to disappear any resemblance of composite origin of this material. So we have literally no optical interface between layers. As conclusions, we found that magnesium ions can be effective as a grain inhibitor, not only like grain role inhibitor, but can help to stabilize microstructure and thus optical properties of ceramic in wide range of temperature. This was demonstrated on the examples of ceramics doped with neodymium and samarium. And then we developed some general approach that can be used at yak-based ceramic with different activators to fabricate composite active laser mediums. Thank you for your attention. That's all. Any questions?
Thank you, Igor. We are open for discussion. The question, please.
Hello, Ito. Thank you very much for your nice report. I have two questions. One is I found the optical transmittance of the anti-doped yak still lower than the theoretical value. So how do you think about what are the main optic loss center?
So again, unity system optical losses in what compound exactly?
Granate with neodymium.
Yeah.
So and magnesium as sintering aids, the optical transmittance is still lower than the theoretical value. So how do you do you think what are the main optical loss centers in your sample?
Main source of optical losses, of course, residual pores. So it's scattering. For our knowledge, there are no secondary phases in ceramics, at least at a microscopic scale. So there are some theories about existence of nanoscaled secondary phases in the grain boundaries, but we cannot confirm it. The main source of losses is scattering at the residual pores. And limiting factor is purity of initial components really here.
So can you see the macropores on the microstructure of the anti-doped yak ceramics? Can you find?
Sorry.
Micropores? Чи бачите ви?
We can see using optical microscopy, we can see pores in size of tenths of micron, and lower pores sometimes can be identified by changes in colorization of image of ceramics microstructure in transmitted light, but it's more indirect. Mostly we can see a pore up to tenths of micrometers.
So why you can't remove those macropores?
Why
So
we can remove?
what's the origination?
You know, it's a pretty fundamental question, really. There are an idea that there are no optimal shape of a grain, of crystalline grain, that guarantees homogeneous distribution of stresses in the grain boundaries. There are always some excess stresses and boundaries due to uneven shapes of grains. And these stresses sometimes releases as vacancies and then pores, which creates which grows from these vacations during sintering, like anti-grains.
I also found at the wavelengths from 200 to 250 nanometer, there is an obvious optical absorption in the end-doped YAG transparent mix. So what's the origination of this absorption?
Sorry, origin of absorption?
Yeah, below 250.
250, it's just like a threshold of conductivity band. It's fundamental absorption threshold.
Maybe it's because of some impurity ions, such as iron.
Okay. It's maybe maybe shifted a little bit because of existence of some bands, impurity associated energy level close to conductivity band. Yes, but in general, it's just the limits of valence like valency band of intermediate garment.
But if the quality of the sample is high enough, there won't be such large absorption.
What do you mean? Sorry, light absorption. It's like zero.
Фланч. Якщо у вас якість кераміки буде вища, то не буде такого поглинання в області 200 та менші.
Yeah, maybe, but you know, it's in fact not so relevant to functional applications of material because the working the diapason of interest, in fact, it's like from 800 to 800 to 1100 nanometers. It's where laser generation of neodymium, terbium, course, and we don't need optical quality at 250 nanometers to be frank.
But I think maybe the absorption will also influence the laser performance.
Sorry, don't hear.
Could you repeat, please?
So can you please repeat the last question?
I think maybe the absorption, even at the wavelengths from 200 to 250 nanometer, will also influence the laser performance of the end-doped YAG ceramics. It's my opinion.
Okay, maybe you're right.
it's complex question. I think it's requires direct testing. It's very hard to judge from general idea, and lots of testing of such materials in only in plans for us for now. We don't provide don't conduct laser generation tests yet for this new composition.
Okay, thank you very much for your nice talk.
Thank you for questions.
Any questions? Okay. Thank you so much. We finished our oral session. And after coffee break, we will proceed with poster session at 20 post 4 p.m. See you soon. Okay.
Добрий день, панство. Мене чути? Добрий день. Добрий день. Мене чути?
Я чую.
Вас чутно.
О, дякую, дякую. Перевірка звуку.
Dear colleagues, it's time to start the poster session. I welcome all of you who joined us at the last poster session. You will have 5 minutes for your report, and there will be no questions at the end. Okay, so we will start with first report according to our program. Olena Lavrinenko from Conseil Institute for Problems of Material Science. Okay, let's wait for when the poster appear.
Do you hear us?
Yeah.
Great. 1 minute. I will demonstrate a screen, and I will make demonstration for all poster sessions. 1 minute, please.
Okay. Let's wait.
Не хоче відкривати. Ага, ну да. Ну, щоб видно, даже.
Do you hear? Do you see my screen? Yeah, great.
Yeah.
Okay. Good evening, dear colleagues. And the fast development of the green technologies, especially in the field of hydrogen evolution and safe environment and cleaning the wastewater, etc., creation the solar cells, etc., requires the formation of new materials with unique optical, catalytical, and photocatalytical activity. Taking into account such tendency, we synthesize the composite based on titanium dioxide modified просто modified with iron and gold part. Colloidal synthesis was applied to the formation of the precipitate and the following the heat treatment results in the performed at 700 degrees result in the formation of the rutile based matrix and with doping of hematite and gold. The general mechanism of the such process lies in the field of the interaction, redox reaction between ferrous iron and orm cations. To activate the catalytical process, we add to our mixture a small amount of anatase nanoparticles formed by destruction of methyltitanic acids. The resulting XRD powders, powders XRD are present on the slide, and the morphology of the such composites are present on the slide too. The catalytical process, we selected 4 dyes. For catalytical process, there was methylene blue, rhodamine blue, orangey, methyl or orange in the concentration 20 milligram per cubical decimeter. And the control on the catalytical process was performed by UV visible spectroscopy. A catalytical process was carried out at 700 degrees within 2.5 hours. On the slide are present the UV visible spectra. In all cases, the chromophoric peaks don't show the shift batachromic or hypsochromic shift, but the intensity of each course step by step decreases. The calculation, the math treatment of the data shows that the decolorization degree of the solution was different, and the best results we obtained for the methyl orange and methylene blue solutions. It was close to 72 and 71% respectively, but for the rhodamine B, the result is worse. Worse is 63%, and the worst result was obtained for the orange G solution, only 47%. The kinetic regularities are present on this figure 3. And the rate constant of the process was changed from 10 to -4 to 10 to -3, and all results correspond only to the chromophore part of the spectra, whereas the aromatic part does not change. Hence, in our opinion, it will be necessary to achieve the full mineralization and the full decomposition of the dye. It is necessary to impact of the UV irradiation, and this work will be continued. Thank you very much.
Thank you so much. Next talk is will be made by Alexander Fedorchuk from Vernadsky Institute of General and Inorganic Chemistry.
Yes, thank you very much. In this work, we are talking about the microwave dielectric ceramics. These ceramics are of interest as dielectric materials for components of advanced communication technologies, from 5 and 6G networks, Internet of Things, to intelligent transportation systems. Consumer electronics have already mastered frequencies up to 5-6 GHz. To master higher frequencies, new materials are needed that meet the following requirements: high quality factor, that means low energy losses, reasonably low dielectric permittivity, less than 20, that guarantees the desired operating frequency, temperature stability, a near zero temperature coefficient of frequency, that eliminates the operating frequency drift caused by temperature fluctuations. Existing materials rarely meet all these 3 criteria simultaneously. Therefore, the current strategy of materials science is focused on the chemical modification of known crystal structures. This report aims to conduct analysis of 2 different but promising classes of ceramic materials: the modified calcium, neodymium, yttrium titanate perovskites and strontium yttrate-based perovskites, spinels, sorry. Calcium titanate-based ceramics are interesting as the compensator for temperature frequency drift in a solid solution with the perovskite structure. And strontium yttrate-based ceramics are interesting as a 5G FRT band material. Both studies utilized the traditional solid-state reaction method. In perovskite, calcium yttrium titanate ceramics, substitution of neodymium ions with the smaller yttrium ions is an effective method for fine-tuning the microstructure and sintering kinetics. This led to a decrease in the unit cell volume and promote the formation of a more uniform fine-grained structure. The introduction of yttrium allowed the optimal sintering temperature to be reduced to 1340 degrees and increased the degree of densification. The optimal sample of these ceramics with the yttrium content 0.08 demonstrates a high dielectric permittivity 104 and high positive temperature coefficient 247 ppm per degree. This material is ideally suited as a component for thermal compensation when mixed with material exhibiting negative temperature coefficient on frequency. For strontium yttrate ceramic, the extraordinarily high quality factor is a direct function of maximum density and minimum porosity. The optimal sintering parameter of 1520 degrees and 4 hours are critical for achieving the near pore-free structure. Partial substitution of yttrium with samarium allowed to reduce the sintering temperature by 40 degrees, which is an economic advantage, but this was accompanied by a decrease in quality factor. The pure strontium yttrate ceramic demonstrates an exceptionally high quality factor. Quality factor multiplied by frequency equals to 92,000 GHz, and low dielectric permittivity equals near 15. With its temperature coefficient of frequency equals to negative 6.2 ppm per degree. This material is an ideal candidate for high-frequency systems with stringent requirements for ultra-low dielectric losses and stability. Thank you for your attention.
Thank you. Next flash poster will be presented by Alexander Vasilyev from Frantsevich Institute for Problems of Material Science.
Good afternoon, dear colleagues. And your attention is a brief report on a DFT study of mixing and vibrational thermodynamics in layered transitional dichalcogenide molybdenum disulfide molybdenum diselenide solid solutions. Why study this? Why look at it from DFT standpoint? The system is interesting in a number of advanced applications, including optoelectronics, photocatalysis, semiconductors with tunable band gaps, specifically because of the possibility to form solid solutions, and by that variation of composition to tune the properties, the band gap properties, and several others. Somehow people looked at the system, at the mixing properties in calculations, in DFT calculations, only for the layered, for single layered structures, never looking at the bulk systems. But in our opinion, it is important to have the knowledge about the system, about the thermodynamics of mixing, about the mixing behavior, and the influence of mixing on vibrational thermodynamics, at least have some good reference, because most synthesis methods for single layer materials or 2D materials would go through the bulk form to some extent or another, or there will be a possibility of formation of such bulk forms. So we didn't find any experimental or computational works for the bulk form, and so we did it in DFT calculation using calculations. I would say it's a series consisting of building a cluster expansion model using a set of DFT data over almost 350 configurations with substitutions of sulfur for selenium. So only mixing only the chalcogenide sublattice. Then using some machine learning methods to fit the model to this data. We also used special quasi-random structures to approximate random alloys and to see how big the influence of possible ordering would be, and to assess the ordering temperature. So the results and vibrational thermodynamics was studied with finite displacement method using quantum espresso or density functional theory as a calculator. So the results are like this. Unlike in the layer system, the mixing in the bulk system is can be considered ideal. We have some degree of ordering, because with the green markers on the figure, upper left figure, the green markers are for the special quasi-random structures, so basically for random alloy, and we see that the enthalpy of mixing is a little bit positive. But there are configurations, especially at the equimolar composition, that show some degree of ordering due to enthalpic contributions. And here we sampled the cluster expansion to see the mixing energies, to calculate the mixing energies for bigger selection of configurations, found the ground state at equimolar composition. You can see that this ground state has chalcogen atoms aligned along specific lines in the structure. But the temperature of disorder transition is pretty low, approximately 190 Kelvin. And surprisingly, or maybe not so much surprisingly, the contribution of mixing into vibrational properties is almost negligible. There are some deviations from the weighted average between the molybdenum disulfide and the molybdenum diselenide. But for all practical purposes, it's very marginal and can be safely ignored. So that's all for me. Thank you very much, and sorry for taking a little bit more time than.
Thank you, Alexander. We are moving to the next poster, Vasilis Limpo. Chernivtsi branch of Ransevich Institute for Problem of Material Science.
Thank you, dear Chairman, esteemed audience. The title of our presentation is 4 types of magnetic subsystems in diluted magnetic semiconductors based on A4, B6 and A3, B6 compounds. We investigated the magnetic properties of 2 types of diluted magnetic semiconductors. Narrow gap cubic tin telluride doped with silicon and manganese, figure 1, and wide gap layered hexagonal indium selenide doped with manganese, figure 2. Both compounds were grown by a modified vertical Bridgman method from chemically pure elemental and binary components. The coexistence of different magnetic phases at low temperatures was revealed. An ordered ferromagnetic phase and magnetically disordered phases of spin and cluster glasses. The starting point for this work was our previous studies of the dynamic magnetic susceptibility of manganese-doped germanium tin telluride, figure 4. The presence of 2 distinct peaks, one of which, on the left, almost does not depend on the frequency of the external magnetic field, and the second one, on the right, does, indicates the existence of 2 different magnetic phases, spin and cluster glasses, in the same sample at a fixed content of magnetic ions. This fact cannot be explained within the framework of the model of stationary magnetic clusters. That is why we put forward a fundamentally new hypothesis. Magnetic clusters are not static but dynamic formations. Their structure is determined by the amplitude of thermal oscillations of the crystal lattice, which gives them the character of quasi-stationary nano-objects, similar to standing waves. The minimum number of Gaussian curves required to correctly fit the experimental curves is 4, figure 1, 2, and 4. This number is not random and coincides with the 4 possible types of spatial objects: point-like, linear, planar, and volumetric. We associated each Gaussian component with a separate subsystem of dynamic magnetic clusters of a certain spatial dimension, which increases together with temperature from 0D to 3D, figure 1, 2, and 4. According to our model, the coexistence of different magnetic phases is a direct consequence of the partial overlap of Gaussian curves corresponding to different dynamic cluster magnetic subsystems. Each of them is described by a set of 5 critical temperatures, figure 3. 2 new critical temperatures, namely T, K, and beta, were introduced for the first time as symmetric analogs of the Curie temperature and the Curie Weiss temperature. The area under the magnetic susceptibility curve, which we called the integral magnetic susceptibility, is a convenient tool for quantifying its dynamics under the influence of external and internal factors. The coexistence of different magnetic phases opens the way to creating spintronic devices capable of using more than 2 logic states. Combining magnetism and photosensitivity within a single crystal makes it possible also to create photomagnetic devices. For example, photomagnetic switches for ultra-fast memory elements and logic elements that operate at pico and even femtosecond speeds, unattainable for classical electronics. So, we have proposed and substantiated the dynamic cluster magnetic subsystems model, which successfully explains the complex magnetic behavior of some cubic and layered diluted magnetic semiconductors, and lays a solid foundation for the next generation of materials for spintronics and infrared optoelectronics. Thank you for your attention.
Thank you. Now we are moving to the next poster. Alexander Voloshin, Institute for Single Crystals, Ukraine.
Good evening.
The topic of my report, morphology and structural perfection of a YAG single crystal and ceramic surface in various processing states. Crystal and optical ceramic of yttrium aluminum garnet summarily YAG due to physical-mechanical properties have a wide range of application in optical laser technology. However, the regulation of formation and evolution of surface morphology and structure at different stages and types of processing, in particular optical ceramics, have not been sufficiently studied. The aim of this view was to establish the features of mechanical and chemical mechanical processing of YAG ceramic in comparison with single crystal and determine the morphology and structure perfection of the surface formed during different states of processing. The simplest for the study was made from the YAG single crystal, which were grown by the HDC method, and from YAG ceramics obtained by the reaction sintering method. Profilometry, X-ray analysis, atomic force microscope, and scanning electronic microscope were used to study the morphology and structural perfection of the surface. It was found that the mechanism of mechanical processing and surface morphology depends on the ratio of the size of the abrasive and the ceramic grain, based on the statistical analysis of the angle distribution function and the support curve. When mechanical processing ceramics with the diamond powder up to 10-7 brittle fracture prevails with further degrees in the size of the abrasive up to 1-0 and chemical mechanical processing, the proportion of plastic deformation during the surface formation increases. For the single crystal YAG, plastic deformation is present at all stages of processing. Within the chemical mechanical processing of YAG crystal, the damaged layer is completely removed and the roughness is approximately 0.6 nanometers. During the chemical mechanical processing of ceramics, the grain structure is being eaten the remains of the diamond background are preserved and the roughness is much higher. Approximately 2.89 nanometers compared to the single crystal. After chemical mechanical processing, the surface of both YAG single crystal and YAG ceramic simples has a perfect structure, as evidenced by the presence of a Kikuchi line, which are identified by more than 75%. Thank you for your attention.
Thank you. The next poster is presented by Olga Beskrovna, Institute for Single Crystals, Ukraine.
The theme of my presentation is upconversion and luminescent properties of calcium fluoride doped with praseodymium ions, microcrystals, and silica xeragel. The development of cell-sterilized surfaces based on stable ultraviolet emitting materials excited by visible light is driven by the need for surface disinfection from viruses and infection without the use of ultraviolet lamps. Praseodymium ions is effective luminescent activator, emitted light in the ultraviolet region by excited at 4F5D level directly or through subconversion processes, which involve converting low-energy radiation into high-energy ultraviolet light by adsorption 2 or more low-energy photons and emitted a single high-energy photon. The calcium fluoride crystalline matrix can be used as a host for doping of praseodymium ions due to its low photon energy, 466 reciprocal centimeters, and high thermal conductivity. However, fluoride materials have insufficient chemical and thermal stability. A composites based on silica xerogels with calcium fluoride nanocrystals doped with praseodymium ions combine the luminescent qualities of fluoride crystals with the thermal and chemical stability of oxide glasses and may be candidates for ultraviolet emitted materials. In our view, calcium fluoride nanocrystals doped with praseodymium ions were synthesized by precipitation method and added to silica xerogel during the synthesis of the composites. The samples were annealed at 600 degrees. The structural, spectral, and morphological properties of the samples were investigated. The X-ray diffraction analysis of the nanocrystal showed the formation of calcium fluoride pure phase and the presence of nanocrystals into the matrix. The measurement of upconversion emission spectra of the nanoceramic under the excitation at 444 nanometers showed that the upconversion emission is in 240 to 190 nanometers spectral region, and the main emission is in the ultraviolet C, 220 to 380 nanometers spectral region. The optical properties of the samples were studied in the visible region at room temperature. Photoluminescent emission spectra of the samples showed two intense emission peaks at 496 and 656 nanometers that correspond to 3P0 to 3H4 and 3P0 to 3F2 transitions. Synthesized microcrystals and composites are of interest for the creation of self-disinfection surfaces on zero basis. Thank you for your attention.
Thank you so much. We are moving to the next talk. Oksana Krylinska, Working Institute for Low Temperature Physics and Engineering, Ukraine.
Good afternoon. The title of my talk is Resistive Switching in Point Contacts Based on Transitional Metal Dehydrogenation. The resistive switching with change of resistance up to 2 orders of magnitude was observed in voltage biased point contacts based on van der Waals transition metal dihalogens such as molybdenum ditelluride, tungsten ditelluride, titanium ditelluride, vanadium disphenide, and other materials. Point contacts were established by touching of a thin wire, usually silver or copper, to the cleavage surface of sub-millimeter transition metal dihalogenide single crystal flake or contacting its edge. The initial resistance of point contacts was about of several tens. That corresponds to submicron size of investigated point contacts. We measured current voltage characteristics and their derivatives, that is differential resistance of point contacts, using the standard modulation techniques in the temperature range from helium to room temperature. The switching shown in left upper figure occurs between a low resistance state that was usually metallic type state and a high resistance state by applying biased voltage up to 1 volt. And reverse switching, that is from semiconductor to metallic state, occurs by applying opposite sign voltage also up to 1 volt. The left bottom figure shows point characteristics switching effect for another point contacts. Point contact measured at different temperature from helium to room temperature. As you can see, the switching survives up to room temperature. Only the amplitude of the switching loop decreases with increasing of the temperature. At the right figure, switching effect is presented for another point contact, measured also at room temperature. And here difference between low resistance state and high resistance state was more than 2 order of magnitude. The origin of this effect can be attributed to the modification of the crystal structure in the point contact area due to drift or displacements, vacancies, or ions under a strong electric field, which is realized in small sized point contacts. Such new functionality of transition metal dihydrogens, which emerges from the switchable domains in semicron heterostructures, looks promising, especially at room temperature, for example, for engineering of non-volatile resistive random access memory and some other application. Thank you for your attention.
Thank you. The next poster is presented by Ihor Biglietka, Iron and Steel Institute, naming after Brussels, Ukraine.
And instead of Igor Lubeka, the topic will be presented by his colleague in Anacorna because Igor is in the business trip now. So, is it okay? Is it okay for you?
Yeah, no problem.
Okay, the topic is morphological features of large paratellurite crystals grown by Czochralski method. In the recent years, there has been a significant interest in growing of large paratellurite crystals for the acousto-optic application, particularly to increase the aperture of the Bragg cells in the image processing acousto-optical filters and for use as a polarizing material. The Czochralski method remains the main commercial method, although it is limited by the furnace size. Increasing the geometry of the furnace has a significant challenge in obtaining large crystals for mass production. Our experiments, which were aimed to obtaining large crystals, have revealed new morphological features on the structure of the crystals. It's something with my screen, or it's okay?
I don't see slides.
It's something with my monitor. What's happened? Oh, yeah, it's okay.
It's okay.
Yeah, sorry, it's something with our electricity line here. So our experiments, which were aimed at obtaining large crystals, have revealed the new morphological features on the surface of the crystals. Our paratellurite crystals were grown by Czochralski method using our original custom-designed furnace. The crystal seeds have a 1-1-0 direction. The grown crystals had a set of morphological forms on their surface, like edge lines and crystal faces. These surface formations were examined by X-ray Bragg diffraction to determine their indexes by standard technique. Sets of 1-1-0 and 1-1-2 planes were observed on the upper conical surface of the crystal. In some previous publications, sets of 1-1-2 planes have been misidentified as 1-0-1 planes. We identified for the first time other planes on the cylindrical section of the crystals, which indexes 221, 223, 113, 114, and 115. These faces varied with the growth conditions. The measured interfaced angles agreed well with the theoretical calculations. These findings suggest that the careful observation of the surface morphology can be used as a diagnostic tool for post-processing analysis of the growth conditions and for the improvements of crystal growth techniques. Further research of these features may provide a deeper understanding of formation defects and help stabilize the growth process of large paratellurite crystals suitable for their commercial applications. For the present, that's it. Thank you for your attention.
Thank you so much. We are moving to next talk given by Alexey Bezdorozhev from Savage Institute for Problems of Material Science, Ukraine.
Dear colleagues, I would like to present the results of our study for the hydrogen reduction of ilmenite from the Malishevsky deposit. As you know, titanium is an important element with wide industrial use. Its main minerals are rutile, ilmenite, and titanium magnetite. Among them, ilmenite is the most important because it makes up the largest share of global reserves of titanium ore. And Ukraine has about from 10 to 20% of the recorded world reserves of titanium ores. An interesting fact is that the most titanium materials are used not in metallurgy, but for producing titanium dioxide, a white pigment used in paints, plastics, ceramics, and other products. Titanium dioxide is mainly produced by chloride and sulfide processes. The chloride process is more efficient, but it requires high quality rutile, which is scarce. That's why upgrading ilmenite into synthetic rutile bioreduction is so important. Instead of carbon reduction, which releases a lot of CO2, hydrogen offers a cleaner solution. The aim of our work was to study how temperature, time, and particle size influences the hydrogen reduction of ilmenite supplied by Vilnohirsky metallurgical plant. The experiments were carried out in pure hydrogen at 750 to 900 at 750 to 950 degrees Celsius for 2 to 4 hours, using both original concentrate and finally ground one. Before conducting experiments, we analyzed the initial ilmenite concentrate and found that it's relatively pure with silicon dioxide as the main impurity. Its average particle size is about 200 micrometers. And for comparison, we also prepared finally ground concentrate with an average particle size of about 10 micrometers. Our results showed that for both samples, the degree of reduction increases with temperature, and after 2 hours at 950 degrees Celsius, we reach almost complete reduction. It was found that for fine concentrate, it was reduced most better, about 10 to 50% more effectively, which can be explained by larger specific surface area. By examining the XRD patterns, we observed that in the case of larger particles, a so-called core shell structure was formed, where an unreduced ilmenite core remained inside, and it was surrounded by reduced metallic iron and titanium dioxide. Furthermore, XRD analysis revealed that the silicon dioxide impurity almost completely disappeared after reduction, and most likely due to gas phase reaction in which hydrogen promoted the formation of volatile silicon oxide and metallic silicon. These side reactions are actually beneficial as they help remove silicon dioxide from titanium dioxide. In conclusion, hydrogen reduction of ilmenite represents a promising and environmentally friendly approach to producing synthetic rutile. Further research will focus on the influence of impurities and the feasibility of separating iron and titanium dioxide. Thank you for your attention.
Thank you. The next talk is given by Olena Makharenko from Savage Institute for Problem of Material Science, Ukraine.
Good afternoon, dear colleagues. The present study focuses on the influence of perovskite-like oxide compounds of barium with scandium and aluminium tungsten on the characteristics of scandium cathodes. Scandium bari cathodes are currently among the most promising materials in terms of emission characteristics. However, they exhibit inhomogeneous emission distribution, low reproducibility of emission characteristics, and unstable durability, which hinder the large-scale industrial application in particle vacuum devices. The reason for this is the use of scandium oxide materials with a wide band gap. Scandium oxide has a band gap of 5.7 electron volt and a high electrical resistivity of 4.4 times 10 for the fifth ohm meters and 1100 kelvins. The aim of the study was to improve the reproducibility of the emission characteristics of scandium barium cathodes. The investigated scandium bari cathodes were fabricated using two methods. First is integration for to produce scary body, impregnated cassettes, and second, deposition of sputtered film containing perovskite-like compounds of the special and the durability were then studied. In this work, we used perovskite-like oxide compounds of barium and scandium characterized by electronic conductivity. The use of a controlled amount of these synthesized compounds during the fabrication of scandium-barium impregnated cassettes and rather than during cassette activation of the interaction of oxide barium and tungsten enables the formation of stable emission characteristics with high reproducibility. The slide presents the current voltage characteristics and the emission parameters of the cassettes, including the electron work function, saturation current density, and durability at specified testing temperature. A comparison with of these cassettes shows that film cassettes figure B exhibit the higher emission characteristics and greater emission uniformity, which can be attributed to the formation of nanoscale structure. For impregnated cassettes, it's figure A. The emission characteristics are determined by the uniformity for the microzone size pores in the tungsten framework. These results indicate that the use of perovskite-like scandium compounds achieved high reproducibility of the emission characteristics on conductive cassettes. Thank you for your attention.
Thank you so much.
Sorry, dear colleagues, our presenter Oksana Kaidash asked the possibility to present her poster now. Is it possible, or we should go up to according to the schedule?
Okay.
Okay, one moment.
Let's move to her poster.
Oh, aluminum powder of first intern. Yeah, here we go. Thank you very much.
Hello, my name is Oksana Kaidash. I am the Doctor of Science from the Institute for Superhot Materials. And today we represented on the result of preparing a statin power system. It compares 2 million techniques based on surface area, impurity level, and structural defectiveness. These factors are critical for fabricating high thermal conductivity aluminum nitride ceramic spots via the pressureless sintering. The estimated quantities of gases adsorbed on the surface of both statin and milled aluminum nitride powders are also reported, providing the essential data for the destination technological routers to produce the dense ceramic components of variable size. During milling in the planetary mill for 2 minutes, the grinding balls remain suspended in the aluminum nitride powder. After 2 minutes of milling, the powder begins to stick to balls and adhere to the walls of the drum, with some grinding balls being eventually pressed into the powder along the high of the drum's walls. After 4 minutes of the milling, the pressed grinding balls begin to detach from the power layer, and after 8 minutes, they are no longer present on the drum's walls. In contrast to planetary mill, no adhesion of aluminum nitride powder to the walls of the grinding chamber was observed in the vibratory milling. The grinding of aluminum nitride powder affects the shape of the particles, particularly those in the form of fibers. which change during the grinding process. After both vibrational and planetary milling, these fiber-like particles becomes faceted. The particle size of the initial power and the powers ground above the vibrational and planetary methods do not differ significantly. The particle size of the aluminum nitride powder after vibration milling grinding range from the 0.4 to the 1 micron and forming aggregates with the size ranging from 2 to 4 microns. After planetary grinding, the particle size range from 0.4 to the 1.3 microns. X-ray structural analysis was used to study the effect of grinding time on the fine structure and lattice constant of aluminum nitride powder in its initial state and after grinding. Dispersion of the initial aluminum nitride power system when comparing two types of milling, planetary and vibratory, primarily depends on the difference in the specific power of the milling equipment. This factor plays a decisive role in the achieving high density, high thermal conductivity ceramic components. Direct electron microscopy studies have shown that milled aluminum nitride powders exhibit increased structural defectiveness. Aluminum nitride particles milled in vibratory mills predominantly contain clusters of dislocation. In a planetary activator, exhibit mainly isolated dislocation. Also, clusters are observed. Thank you.
Thank you very much. We are moving to next talk. Alexander Voloshin, Institute Single Crystals, Ukraine.
The topic of the report is peculiarities of a mechanical response of sapphire under non-indentation. The enormous interest in the physical mechanical properties of materials at the nanoscales has stimulated the development of a new approaches to mechanical testing. The non-indentation method allows us to study hardness on the qualitatively new level, in particular to analyze the specific of elastoplastic transition when in a nanocontact. Sapphire is one of the most common structure material. In this work, the specific of elastoplastic transition in sapphire obtained by the method of Keropoulos, Shakharsky, Stepanov, as Werneris have been studied. The studies were carried out on a crystallographic plane C, 001, A11 minus 2 O and R 01 minus 1 2. Studies were fulfilled on the mechanically polished surface on the simplest on the mechanically polished surface followed by the high temperature annealing and on the chemically mechanically polished surface. And the indentation was performed with a Berkovich diamond pyramid. The indentation depth was 100 nanometers. In the curve of indentation of Berkovich indent into the single crystal, an abrupt transition from the elastic to plastic deformation has been observed at the depth of about 7.5 nanometer due to the nucleation of dislocation in the initially dislocation-free zone under the contact. The transition has been caused by the homogeneous nucleation of dislocation under the imprint in previously dislocation-free region. The characteristic of elastic plastic transition in crystal with different density of groove dislocation were obtained. Our studies show that the elastic plastic transition in non-contact of perfect crystals such as Chiropoulos crystal occur at a much greater depths and loads than an imperfect single crystal such as vernalium crystal. It was been established that the anisotropy of nano-hardness is lower than the anisotropy of the ultimate hardness. Thank you for your attention.
Thank you very much. We are moving to the next talk. Андрей Прокопов, Institute for Synthetic Materials.
Dear colleagues, I'm pleased to present my report on tungsten-based scintillators for next generation colorimeters for high energy physics. The work has been carried out in collaboration with co-authors from the Institute for Scintillation Materials of the National Academy of Science of Ukraine, Kharkiv, and University of Paris-Saclay, France, and the Granite collaboration. Modern high-energy physics projects such as the Future Circular Collider at CERN require detectors combining high resolution, fast response, radiation resistance, and cost effectiveness. Traditional bulk single crystals have limitations. Their growth is slow and expensive. As an alternative, composite detectors of the granite type are under development. They employ granular active volume consisting of metal tungstate micrograins with high Z embedded in transparent matrix. In this configuration, scintillation light is localized and effectively collected by optical fibers. The approach improves resolution and enhances measurement accuracy. Our contribution focuses on materials, developing technologies for producing scintillation crystal grains of divalent metal tungstates and their solid solutions. For grain production, the flux growth method was applied, allowing formation of microcrystalline grains such as zinc tungstate, calcium tungstate, and others. This method ensures higher yield, controllable grain size, and good optical quality under nearly gradient-free temperature conditions. Sodium tungstate was used as a solvent. The developed technology provides a yield exceeding 80% of the initial charge mass. Studies confirmed that zinc tungstate grains have monoclinic wolframite structure. Their X-ray luminescence spectrum is nearly identical to that of bulk crystals, with only slight redshift due to self-absorption. The X-ray luminescence intensity is about twice higher than in bulk crystals. Photoluminescence spectra of grains show no defect-related bands observed in bulk zinc tungstate, while decay time remains the same, around 25 microseconds. It was found that crystal lattice of calcium tungstate grains corresponds to tetragonal scheelite structure, which is characteristic of calcium tungstate crystals. Their luminescence spectra match those of Czochralski grown crystals, and the decay time is about 9.5 microseconds. For the first time, mixed crystals of calcium lead tungstate were obtained. They show higher density, a 3 times shorter decay time than calcium tungstate, and X-ray luminescence reaching about 80% of calcium tungstate. The structure was confirmed to be tetragonal scheelite. At University Paris-Saclay in France, many prototypes of the granite detector were built using our experimental batches of zinc tungstate and calcium tungstate scintillating grains. This prototype is called the Troll. Cosmic muon tests show that calcium tungstate grains provide 60% higher light yield and twice faster decay compared to zinc tungstate grains. Such properties make calcium tungstate a promising material for future detector development. Our main results and conclusions are flux growth conditions were developed for zinc tungstate and calcium tungstate grains, ensuring luminescent properties comparable to Czochralski crystals. Optimization of growth process eliminated defect centers, which resulted in about twice high X-ray luminescence intensity. The developed growth technology ensures a yield above 80% of the initial charge. The granite detector prototypes confirmed the superior performance of calcium tungstate grains, showing about 60% higher light yield and about 2 times faster response. Mixed calcium lead tungstate crystals were obtained with higher density and roughly 3 times faster decay. Thank you all for your attention.
Thank you for your nice talk. We are moving to the next poster. Alexander Sorokin, Institute for Scintillating Materials, Ukraine.
Hello, colleagues. Let me introduce our results. Currently, except classical scintillation materials based on large-scale crystals or large-scale, for example, plastic or organic materials, nanostructured materials used for scintillation detectors are also attract a lot of attention, and the term nanoscintillator is begin quite very popular because such materials can provide some benefits, like, for example, much less cost of production and so on. And one of them is the prevention or is the exciting properties of such nanomaterials, which couldn't be obtained in large-scale crystals. For example, one of the very popular currently studied materials is so-called perovskite nanocrystals, which was already shown their very interesting properties, especially when embedded in different polymer films. And it was already shown their possibility to use, for example, for X-ray detection. They are very interesting that the structure of and composition of such nanocrystals could be varied. For example, it could be obtained in different forms, and depending on their anionic composition, it could be provided the luminescence band in different range of the spectrum. And it's very interesting that it could be easily to embed in different polymers films. One of the best materials appeared polymethyl methacrylate films, and depending on the composition, it has quite fast luminescent decay, with the decay time decreasing from the bromide nanocrystals to pure chloride nanocrystals. And that is the most important, that such behavior also was proved by measurement of the scintillation decays, and also for the best composition, we obtain sub-nanosecond decay time, and it's a very promising way for the development of very fast scintillator materials, which needed for example, medical devices where time of flight detection should be very small, and also for the next upgrading of Large Hadron Collider in CERN. Thank you for your attention.
Thank you so much. We are moving to the next report. Mark Vovsyannikov, Institute for Single Crystals, Ukraine. Good afternoon. My name is Mark Vovsyannikov. I'm a PhD student in Institute for Single Crystals of National Academy of Sciences of Ukraine, and my supervisor is Dmitro Vyacheslamovich. I want to present results of charge impurities in YAG investigation based on DFT calculations, and the time is quite short, so time is quite short, so I want to emphasize only one thing. The main thing from motivational part is that there are experimental works shows possibility to use tightened yttrium aluminum garnet for applications, mainly lab applications. But researchers encountered some problems, some challenges. For example, increased number of inclusions under oxidizing sintering for ceramics and growing for single crystals conditions. That creates some space for further investigation in this field. And you may see on the bottom of our introduction part that it was our main goal of our current work to find problems and defects, and in general understand how the concentration of each defect type depends on sintering and growing conditions. We have calculated defect formation energy with the equation you may see on the top of calculation methods part. There you can see pristine yttrium aluminum garnet formation energy and formation energy for yttrium aluminum garnet with given defect. We have obtained their values with using the CSS software package, performing DFT calculations, and next, chemical potentials of atoms were calculated considering the formation energy of compound and the sum of chemical potential of atoms in its composition. We have considered 10 equilibrium points. You may see them on a diagram in the middle of calculation methods. far. 6 points for aluminium to oxygen 3 rich condition, and 4 points for excess of yttrium 2 oxygen 3 conditions. Then we calculated concentration of titan and in general concentration of defects with the given formula on the bottom of the calculation method part. And this value is given in atomic percents relative to the total number of atoms in the YAG unit cell. It was 160. Also, we've taken a temperature, incident temperature for yttrium aluminum garnet for these calculations. And according to our calculations, you may see these results on figure 2. According to our calculations, we have found that titan almost doesn't incorporate in lattice as interstitial ions. Their value were, as I remember, less than minus 10 atomic percent, minus 10 order atomic percent concentration. And substitutions, titan yttrium substitutions also doesn't show big numbers. So as you see, only on intermediate conditions, they have the maximum number, but it's also quite small. So we haven't considered their complexes with another defects. So the main defects that titan forms in yttrium aluminum garnet according to our calculations is titan aluminum substitutional defects. And the main point in this context is that titan can be in the titan 3 plus and titan 4 plus valence states. And it highly depends on conditions. So as we can see, if we talk about reducing conditions, mainly titan incorporates in lattice in 3 plus valence state. And if we talk about oxidizing and even intermediate conditions, titan incorporates in mainly 4 plus state. These results are in agreement with experimental studies, but in experimental studies, researchers considered just a few possible points, just a few possible options of growing conditions, and we can consider much higher, much bigger range. So we can notice that in intermediate conditions, concentration of such complexes as titan 3 plus and titan 4 plus, as example, is increasing. That also may be quite interesting for producing such materials. Also, we have calculated band structure for titan TIAC, and as you also can see, mainly for titan aluminum substitution defects, they form bands, they form transition levels in interval between 3 and 5.5 electron volt, and levels in 0 and 1 and 5 electron volts associated with cation vacancies. That is also in agreement with another studies on yttrium aluminum garnet. And our main conclusions, that part of them I have already described, and maybe yes, the one thing I haven't noticed, that doping of titan leads to increase in the concentration of free cationic vacancies, and in this situation they play a role of
the role of charge compensator for Titan in 4+ valence state. And that's all. Thank you.
Thank you, Mark. Now we are moving to the principal. Irina Rybakova from Institute of Simulation Materials, Ukraine.
Good afternoon. Dear colleagues, I would like to present our work aimed at R&D halcogenide scintillation materials for rare event search experiments. Today, one of the current areas of nuclear physics is experiment to rare event search, for example, the dark matter search and neutrinoless double beta decay. In the last decade, to study rare nuclear processes, along with collider experiments, the method of low background nuclear spectrometry using cryogenic scintillation phonon detectors has become widespread. This method makes it's possible to obtain separate phonon and scintillation signals and provides a low recall energy as a result, high energy resolution, and efficient separation of events. The main requirements of scintillators are extremely low level of radioactive contamination, high light output at millikelvin temperatures, the presence of a specific nuclear, as well as high optical quality and perfect crystalline structure. In this work, we present the result of research aimed at developing and improving halcogenide scintillation crystals based on zinc selenide, zinc telluride, and mixed compounds zinc selenide, zinc sulfide for low background cryogenic detectors. We have developed a method for the synthesis of high purity starting materials and tested optimal modes for these crystals growing from the melt using the vertical Bridgman method under high argon pressure. I will present the main conclusions obtained in this work. It has been shown that halcogenide scintillators such as zinc selenide and solid solutions based on it and zinc telluride are promising for use in low background nuclear spectrometry. This idea has already been implemented for the first time on enriched zinc selenide with isotope selenium-82 in Cupid 0 detector. Testing of which is successfully continuing in the experiment to neutrinoless double beta decay in Grand Sasso laboratory. For this experiment, an original production technology was developed and low background enriched zinc selenide crystals with isotope selenium-82 were grown for the first time. It was been shown that at a temperature about 5 Kelvin, for zinc selenide, a luminescence band of bound excitons is observed. It has been established that this band is the most intense. It controls zinc selenide doping with aluminium. This property has been implemented in cryogenic low background detector. For the first time, the thermal conductivity of zinc selenide crystals was studied in a wide temperature range of 5 Kelvin to room temperatures. It was established that the length of unknown Fourier path at low temperatures is about 20 microns, which is comparable to the distance between the boundaries of twins in the crystal, which can affect the phonon signal of the bolometer. For the first time, zinc selenide, zinc sulfide book scintillation mixed crystals were obtained for low temperature studies of scintillation parameters. zinc sulfide concentration range in these crystals was from 5 to 30 atomic persons. It was found that with an increase in zinc sulfide content in the mixed crystal to 15 atomic persons, the light output increases by 1.5 times relative to zinc selenide doped tellurium. It was shown that at temperature below 150 Kelvin, there is an increase in the light output and a decrease in the decay time of mixed crystals, which indicates the prospects of their use in cryogenic scintillation detectors. And the last, it has been established that at a temperature below 120 Kelvin in zinc telluride crystals, a luminescent band with the maximum 580 nanometers is observed, which is quented at room temperatures. A significant increase in the light output at low temperatures was shown more than 4 times, and it was suggested that zinc telluride crystals could potentially be used as a cryogenic scintillation bolometer in experiments to neutrino-less double beta decay search of isotope tellurium-130. Thank you for attention.
Thank you, Irina. Now we are moving to next talk. Serving to the show. Vernadsky Institute of General and Inorganic Chemistry, Ukraine.
Good evening, colleagues. In response to the growing demand for new materials capable of withstanding extreme conditions, our work focuses on efficient electrochemical synthesis strategy of tantalum silicide. Today, there is a wide range of methods for synthesized tantalum silicide, but despite the advantage of each of these methods, they have a number of limitations, including the need to use high temperature specialized equipment, the complexity of the process, and low deposition rate for some methods, and the possibility of the formation of unwanted phases. The method of electrochemical synthesis in MELS has a number of advantages over the synthesis method uses. It's lower temperature than indirect synthesis methods, economical efficiency, and the possibility of obtaining both powders and coatings. Thermodynamic calculation and voltametric analysis clarified the reduction mechanism, confirming the sustainability of chloride-fluoride methods. Using the multiple source electrodeposition in chloride-fluoride systems, we investigated the formation of tantalum silicide. Electrolysis on nickel cathodes produced both powders and coatings, whose phase composition and morphology were confirmed by XRD and CAM. We observed that current density plays a decisive role. At higher density, porous dendritic powders formed, while at lower current density, dense coatings with globular features were obtained. This result demonstrates that electrochemical synthesis offers precise control over phase and morphology, making it a promising pathway for producing tantalum silicide for microelectronics, protective coatings, and high temperature application. Thank you for attention.
Thank you so much.
Hello, dear colleagues.
Yes,
It's my
to next talk, Serhii Lakiza, Ensemble 3, Center of Excellence, Poland.
Yes, I'm Serhii Lakiza. I work in Francevich Institute, but at the moment I'm on the so-called internship in Poland, Warsaw Institute Ensemble 3. Its long name is shown here at the right corner. Yes, so the results of my investigation is shown in this triangle. What is this? It's the liquidus projection of iron, selenium, bismuth phase diagram. Why? Because the main idea of Ensemble 3 is to study the properties, especially photonic properties of eutectics. But when we speak about eutectic, then another word stands near. These are phase diagram, because on the liquidus we see the coordinates of these eutectics, the temperature and composition. So the most interesting phase eutectic in this system is ferrum 7, selenium 8, and bismuth 2, selenium 3. Here in abstract we see the obstacles. Why do we use these? Why do we investigate these eutectics? But the investigation of liquid surface discover us that in this system we have two triangulating sections. This one and another one. Iron with selenium 8, bismuth 2, selenium 3. So we have two binary eutectics and one ternary eutectic. Here's binary, and among them we have one ternary eutectic. It consists of three phases: iron, bismuth 7, selenium 8, and bismuth 2, selenium 3. Oh, sorry, iron 7, selenium 8. So these are the results. Yes, and that's all that I want to tell you.
Thank you for nice talk. We are moving on. Sorry. Valentina Ivanitska from Chernivtsi National University, Ukraine.
Thank you very much. Good evening, dear colleagues. The topic of our study is solution of dimethyl sulfoxide cyclohexanol system for cesium, plumbum, bromide surface treatment. Recent scientific research shows that the surface treatment of cesium, plumbum, bromide perovskite is a very complex process. Metal halide perovskites, which have great potential for use in photovoltaic devices, are characterized by significant chemical activity and degrade under the influence of water, oxygen, etc. All this points to the need for systematic research and the search for methods of high quality and defect-free surface treatment of perovskites. The aim of our study is to investigate the effect of perovskite surface chemical treatment on its surface properties. Perovskite samples cut from the ingot were used for the experiment. The plates were mechanically polished. After polishing, samples were glued on quartz substrates with the help of wax. Chemical treatment was carried out using the special equipment figure 1. The rotation, the samples were fixed in the disc-shaped Teflon holder on the device. The rotation speed of the Teflon holder in the solution, in the agent, was 90 rotation per minute. When determining the limited stage of the dissolution process, this speed was varied from 30 to 130 rotation per minute. The etching rate was determined by the decrease in the thickness of the samples after etching. The etched and washed samples were dried with a stream of compressed air. In the first stage of the study, the material removal rate in dimethyl sulfoxide cyclohexanol solution was measured. Cyclohexanol was added to dimethyl sulfoxide to reduce the dissolution rate of the samples. Figure 2 shows the dependence of the remote layer thickness on the etching time, as can be seen from the dependence. The addition of cyclohexanol to dimethyl sulfoxide significantly reduced the etching rate of perovskite. At the cyclohexanol content of more than 50 volume percent, the dissolution rate decreased to almost zero. After etching perovskite with solution containing more than 50 volume percent cyclohexanol, the surface of the samples deteriorated significantly. Therefore, we consider that the solution of this composition is not suitable for future investigation. Addition of 30 volume percent cyclohexanol to dimethyl sulfoxide does not lead to deterioration in the samples of surface quality. Therefore, if the goal is to remove the surface layer of perovskite at a low rate, the methyl sulfoxide with up to 30 volume percent cyclohexanol can be used. The next step, figure 3, the next step of our study was determination of the dependence of perovskite etching rate on the rotation speed of chemical dynamical polishing device disk. Determination with dependence make it possible to predict the mechanism of by which the process occurs, diffusion or kinetics. For the study, the 30 volume percent solution of methanol in dimethyl sulfoxide were used. Since extrapolation with dependence to the ordinate axis cuts off certain segment of the axis, it is possible to assert that the process of perovskite dissolution in our study solution occurs according to the mixed diffusion kinetic mechanism. Therefore, summarizing all of the above mentioned, we can conclude that first, dimethyl sulfoxide can be used to treat the surface of perovskite, provided that substances are added to their composition that slow down the rate of dissolution of the material. Addition of 30 volume percent of cyclohexanol to dimethyl sulfoxide reduce the dissolution rate of perovskite more than twice, and dimethyl sulfoxide cyclohexanol solution interact with the perovskite surface through a mixed diffusion kinetic mechanism, which indicates the prospect of their use in the treatment of the cesium plumbum bromide surface. Thank you for your attention.
Thank you very much. Next talk will be given by Pavlo Konevsky, Institute for Single Crystals, Ukraine. Please.
Hello, dear colleagues.
Today, I would like to present a development of technique for creating magnetic structure from synthetic sapphire. This research was done to produce suspension for the mirror in the gravitational telescope that named LIGO and its new modification with bigger mirror that named Einstein. This work done together with company Impex HighMatTech from Germany. Sapphire has the remarkable properties of strength and heat conductivity at temperatures around 30 Kelvin. Traditional method of joining composite sapphire structures offering structural and property reliability only within restricted temperature range. Our goal was join sapphire components using their own melt. So we want to create a truly monolithic sapphire structure. The process begins by forming a capillary channel between two sapphire single crystals that are to be joined. This channel filled by wetting action of molten sapphire followed by controlled crystallization. To monitor and optimize this process, the temperature of joining was tracked using optical pyrometry, while the melt movement and subsequent solidification within a capillary channel were recorded using high-speed camera. To accurately describe this phenomena, the theoretical model was developed, focusing on capillary rise of molten sapphire in sapphire channel. This model applicable under specific growth conditions, specifically a vertical temperature gradient of from 50 to 100 Kelvin per centimeter. The tests of theory was made on plain capillary channel, and the melt was observed in the channel with width from 0.5 to 0.1 millimeter, and melt moved up to 28 millimeters. Frames from high-speed camera were analyzed and speed of melt rise were calculated. The optimal width for capillary channel was found from modeling experiments, and sapphire suspensions for the mirror were produced. You see this sapphire suspension, they are created of three parts, two blocks 20 by 20 by 10 millimeters, and rod 3 millimeter in diameter. The length of such suspension can be up to 550 millimeters. In experiments, the crystallization rate was measured in both planar and cylindrical capillaries, 37 to 90 millimeters per second, and 120 140 millimeters per second, respectively. The observed melt movement velocities are in good agreement with the theoretical model of capillary-driven melt flow. The tension stress testing for sapphire suspension were done, and the load of failure for the samples were up to 260 megapascal. It shows a potential of high strength for assembled sapphire suspension using sapphire melt. It's about 70% of maximum strength of sapphire. That's all. Thank you for your attention.
Thank you, Pavlo. We are going to the next stop. Оксана Матвієнко, Institute for Single Crystals, Ukraine.
Hello, colleagues. I'm excited to present our research on the effect of high-energy Wolff-Milan condensification peculiarities of reactive cinchers Yag-samarium ceramics. Today, Yag-samarium transparent ceramics have been one of the most perspective cladding materials for suppressors of parasitic oscillation in high-power Yag neodymium lasers owing to its exceptional optical characteristics. Well known, the densification rules of reactive sintered ceramics materials are heavily preparation dependent. Structural and morphological characteristics of starting powder determine the mesostructure of grain bodies, sintering rates, and structure of final sintering ceramics. The high-energy ball milling processes allows to reduce the particle size of starting powders to control particle size distribution and to break up agglomerates, thereby enhance optical uniformity and increase ceramic transmittance. This work is devoted to optimization of ball milling processes of Yag-samarium powder mixture in order to improve optical homogeneity of transparent ceramics. The milling rate of Yag-samarium powder mixture has been drawn up using median particle diameter and width and skewness of particle size distribution obtained from dynamic light scattering method. As can be seen from part 3 of poster, with the increase of solid loading from 20.8 to 21.5 %, the median particle size reduced drastically from 0.77 to 0.54 micrometers. With further increasing the solid loading, the particle size gradually increased and median particle diameter reached 0.7 micrometers due to the process of secondary particle agglomeration. The all samples versus solid loading are similar in the width and skewness of the particle size distributions. As observed from part 4 of poster, with increasing milling speed from 100 to 120 and more RPM, a significant reduction of median particle size from twice occurs. The secondary particle agglomeration begins to occur at a speed of 160 RPM. In the 120 to 130 RPM speed range, skewness values are almost constant. The less data are in good agreement with same data. The grain bodies obtained with the solid loading in 21 and 5 to 20-third volume percentage at 120 and 130 milling speed exhibit similar density of about 47% after annexing operation and 57% after call as a static pressing. The slide on the right showed typical some images of the planetary ball milling Yag-samarium powders obtained in optimized and not optimized milling parameters and corresponding surface morphologies of reactive sintering ceramics. High optical transmittance above 83% at 808 nanometers is observed for all ceramic samples prepared from the planetary ball milk mixture prepared at 120 RPM with solid loading at 23 to 21.5 volume % range. The decrease in the transparency in Yag-samarium ceramics with an increase in the milling speed from 160 to 180 RPM is explained by the increase in the microstructure reducible porosity due to the intensification of the secondary agglomeration effect of the powder mixture. This work was supported by the National Research Foundation of Ukraine. Thank you for your attention.
Thank you. Next talk will be given by Sergei Vilanova, Institute of Single Crystals, Ukraine.
Thank you. Dear colleagues, I present to your attention a report fine optical and structure inhomogeneity of supply ground in different methods. Improving the functional characteristic of optic and laser elements requires the production of crystal with structure perfection, and high optic homogeneity. The key factor determining the performance of crystal structure defects, non-uniform impurity distribution, or inhomogeneity in dislocation structures. In parallel polarized light in an alternation of dark and light narrow strips is observed. This can be tentatively attributed to the variation of refractive index due to the presence of alternating microregions of potential compression, or possible to the presence of polygonal dislocation boundaries with small misorientation angles. The strips strictly oriented parallel to the 001 plane. In some cases, the formation of strips corresponding to the interaction of the studied surface with the plane 11-20 or 10-12 observed. The location of the bands isn't related to the dopant concentration distribution, the shape of the crystallization front, and doesn't depend on the crystallographic direction of crystal growth. The contrast and homogeneity of polarization optical pattern correlated with the dislocation density and the level of reducible stresses characteristic of the growth method. In some cases, as said, as such strips, packs leads to the appearance of optical inhomogeneity of crystal with WFD with an amplitude up to PV approximately lambda by 4 at 633 nanometers, what is associated with slip bonds. Slip in a crystal occurs along specific crystallographic planes and directions. They are usually the most densely packed atomic planes and directions. Slip along them occurs with minimal disturbance to the arrangement of atoms and therefore in easiest. By the method X-ray diffractometry, it was shown what from the 30-30 reflex in contrast to the 00012 reflex. Not only the bouldering of diffraction reflection curves, but also fragmentation into several peaks is observed, which may indicate the presence of polygonal dislocation boundaries in the 10-10 plane with misorientation angles approximately 1.5 second and 2.0 second. As a result of research, it was established what the formation of bonding substructure occurs at the initial stage of crystal cooling at perimeter temperature as a result of self-organization in a dislocation subsystem during the plastic deformation is an easy slip plane 001 under the action of thermoelastic stresses. One of the factor contribution to information is a possible structural transformation in the 001 plane of all ions under the action of electrostatic interaction forces at high temperatures, and the formations reaction based on all layers. Thank you for your attention. Thank you very much. And we are going to the last talk of our symposium. Ivan Lushny, Sarcevich Institute for Stock Material Science, Ukraine. Are you here?
Probably not. Ivan, are you here? Are you hear us?
Alexander Yakimchuk should have been present for this presentation.
Alexander Yakimchuk. Okay.
But I'm not sure if he is here. It's Alexander Vasilyev speaking.
Okay, so
Alexander Yakimchuk also absent.
Yeah.
Yeah, maybe absent. So I have some words to summarize our work. Yeah. First of all, I'd like to thank all of for the speakers for your valuable contribution to the symposium functional optical materials. I think it was successful because we have only one report cancelled. Yeah, it was total 22 posters in the poster session, and we have 14 oral reports, including 2 keynotes reports and 4 invited reports from Ukraine, China, Italy, Germany, and France. I hope to see you next year at the same conference, which will be a Jubilee conference, 10th HighMatTech conference. See you next year. Thank you very much.
Thank you very much.
Bye-bye.
Bye.
Bye. Давай пока.
Bye.